Um, Welcome to the session 10 of the masterclass in audio. We resume where we left off at session 9 with two giants of audio and acoustics, Ron Sauro and John Brandt, the third. So, as always, like the previous session, I'll allow Marsban to just lead the session. But just to set the protocols for the session, I have mentioned that in the chat window. I request everyone, barring the four of us, to mute your audio and also turn off your video. And questions can be posted on the chat window as and when they come into anyone's mind. If there is a relevant question at any point of time, I'll pose that to John as well as Ron. And otherwise, the questions can be posed towards the end of the session. So yeah, over to you, Mazban.
So guys, welcome again to another session of Masterclass with all of us. Today we have, again, our two top guys, John Brandt and Ron Sauro. And this time, John's going to be taking the lead. As you all know, John has been in the music business right after high school. He was an FOH engineer, and he's also worked with ex-Fleetwood Mac member Jeremy Spencer, who's his friend today. He also toured Europe in the 70s until 76 when he moved to the UK. Am I right, John? I saw you grimacing.
Yeah. Let's see. It was 76. Yeah, 76. It was 76.
And then you started your electronics and acoustic studies in the UK in 76. And also you ran sound in a lot of clubs.
Acoustics and electronics way before that.
Yeah.
Getting books and making stuff. Yeah.
So great. So anyway, John's very, very experienced in studio design. That's his main forte. Actually, listening space design. He also designs large spaces like, stadiums and auditoriums and studios. In fact, aren't you shortlisted for one of the most largest mosques in the Middle East? Isn't that what you?
Not a mosque. No. They contacted me as acoustic designer for a music King Faisal music center. It's huge. It's absolutely huge in Saudi Arabia. We'll see. I've got three companies actually asking me if I would be their acoustic consultant. So I just sent them all the same thing, basically. We'll see. So I've got three lottery tickets instead of one. We'll see what happens.
That's fantastic, John. But today what we want to discuss and where we left off is home theater design. And we want to understand your process, how you go about it. What are the basic room ratios that you'd like to use, which really give you good results? What are the kind of acoustic treatments that you use? Where do you place them in the room? What are the basic calculations that you need to get out of the way? And then after, how do you choose loudspeakers which go into these rooms? Their dispersion patterns, their what do you call it, in their horns, their directivity and stuff. And also the constant argument of quadratic residue diffusers, scatterers, reflectors. How does one choose what's best for a particular room to end up with really a great sounding home theater room? I know yes, stereo is also around, but since a lot of us in this field, specialize or do a lot of home theaters rather than studios and stereo listening rooms, we wanted to take up this topic because I know it's endless, and you could take it up from your thought process and how you start off on a blank sheet, okay, and how do we go from there?
Okay. Starting off first, of course, we discussed a little bit on soundproofing last time, right? So once you have your place soundproofed enough so that you're not disturbing anybody and they're not disturbing you, we start with, we go, well, you got to figure out room ratio first. And it's not just the ratios, because ratios as they are, you can look at the Sepmeyer, or the Loudon or the Bolt or whatever. They don't just work out of the box. You have to, they'll get you close, and then you have to run the numbers in a good calculator. And what I do, if you don't mind, I'll share, for example, I'll share a room mode calculator. This is available on my resources page. You just download it, either metric or imperial. Since you guys are imperial and most people in the States are imperial, I'll run an imperial one here and share. Here's one, for example. Let me just share my screen here. I got this ATEM I can use. Let's see. So we don't need that. Here's a the what you call it. All right, let's say we want to put in these numbers. Now this one's already calculated for something, and I've done a little algorithm here that tells if the frequency or the mode above this one is too close to it. So this one is 0.3 hertz, but it's an oblique mode. And obliques are so weak that I kind of disregard them as far as problems with axial. So I'm looking for axial and tangent issues. So this tangent is close to the oblique, so it's not going to cause a drone or a resonance issue. This axial right here at 133.8 will most likely cause a droning at 133 hertz. So this is less than optimal. So anyway, we go to the ratios. We can look at Bolt is one that is commonly referred to in as the go-to ratio. However, using these hardly ever works out of the box. I mean, you can plug in these numbers. Nope, no go. Even sometimes they won't even meet vanilla. So you have to play with it a little bit. Sepmeyer 1 and 2 are often, they quite often do work right out of the box, but you should play with them. Like, for example, let's say we have a 10-foot ceiling. So that's 120 inches. And we look at, let's take Sepmeyer 1. We got 158 square feet area, and we just squeeze past the bare minimum of 1,500 cubic feet, which is 42 cubic meters for the metric. So let's plug in these numbers. It's like I need to write them down because I've got a mind like a steel sieve. If I look at these numbers, they won't stick.
So the question that I've always wondered in all these calculations is, are these figures of length, breadth, height, the bare shell, or this is after you've done your isolation?
This is the inside finished dimensions of the room. Okay.
This is after acoustic treatments also?
No. The acoustic treatments won't change the basic resonances. Now, there's been some arguments about that where, because that's how fiber trapping, or when you have broadband absorption in the room, the way it works is it slows down that wave. It slows the propagation of the sound wave, slows it down. Okay, so if you add all that up, it will change very slightly your resonance, but it's not enough to worry about. I've ever experienced, never changed it enough to change your membrane traps that are tuned to a primary modal resonance. No, it doesn't change sound, the speed of sound. Like, for instance, if you think it changes the speed of sound, put rock wool on your ears and listen to music and see if it is going slower. It doesn't. It's not, but that's the mechanism that is used to absorb, to turn it to heat. The process, it's the inertia hitting a mass and bending it, and that causes attenuation, absorption. Ron can make it a little more clear if I'm going out there, but anyway, let's go back to the room mode calculator. So
we can cover some of this later on how absorption actually works.
Right. I just wanted to I just wanted to say a little something about the slowing down of the sound wave. That's part of it, but it's not going to affect your resonances. You want to do your calculations based on the finished interior shell. I mean, that's with all the drywall and whatever you're doing for soundproofing and finishing. Okay. So we're going to start with, I run that calculation. We got 120 here, 137 here, and 167 here. All right. And then I'll do the macro function of this calculator, and we have a problem here. See this? 98 and 98. That's point, says it's 0.1 hertz apart, but maybe there's little discrepancy between these two, but that's a resonance there. That's a problem. So we have to change the width so that we could make this either go lower or higher. So we could make it wider or narrower. I'd rather go a little wider. Let's try an odd number like 141. See what happens to that axial. See it push that problem away. So our next problem area is right here at 169, almost 170 hertz. Let's see, our Schroeder frequency is 152. It's well past it. I'd like to see it get up to 216 before we hit any problems, but honestly, this area here, where did I have it? Where was it? This 169 is definitely trappable. And what I want to avoid is anything below the Schroeder frequency of the room that causes a resonance, because you're really not going to be able to trap it, as far as that, at least in my experience.
John, you might want to explain what the Schroeder frequency is and how to calculate it.
Okay, here is the calculation. The calculation is built into this, but the calculation is, ta-da, speed of sound, and what's it, D7. I'm gonna have to go back to this and look at this. This is the square, the cubic feet of 102. In 102 is, oh, that's a hidden thing. No, it's not. 2. Okay, so that's the mean free time, or the decay in the room. The decay spec, which is another calculation. It's based on all that. And that'll tell you where you have basically the wave region breaks into the diffusive region. And it goes up to, in this room, it'll go up to 600 hertz. And then that breaks into the ray region. And from 600 to 650 in this area, this is never abruptly defined. It's about here. According to the calculations, it's here. But you can count on any frequencies from this and up to be pretty much laser beam, okay, as far as the way they bounce.
Yeah, guys, just so you're aware, I'm sorry, John, to interrupt you here, but make it a little simpler. There's two methods of calculating sound out there. One is called ray tracing, and the other part is wave theory.
Yes.
Okay. Ray tracing is based on light. So if you have reflections coming from certain places, they follow Snell's law, pretty much. Okay. When you get into wave theory, now you get into the idea that the wave is larger than the surface you're looking at, and therefore it may or may not see the surface. So it may go around the surface like water would go around up here. And that's the difference. So that's what you're looking at, is where in the room, at what frequency does the light theory stop, which is what most of the modeling programs use, versus wave theory, which is what FEM uses, BEM, stuff like that. Okay.
Yes. So it's really is from 153 hertz here down to the lower frequency wave limit of the room, which is 40 hertz in this room. This is a small room. It's this is the smallest room you really want to. If you're building something, don't build it any smaller than this.
When you say the wave limit of the room, do you mean the lowest frequency that is audible in that room?
Not really. No. You can hear stuff if it's reproduced. Here's the trick. If you can reproduce a wave in the room of this size here, below 40 hertz, say 30 or 25 hertz, if you can reproduce it, you can hear it. But the thing is, if you have a ported loudspeaker, the box tends to kind of dissolve and disappear past this region where the actual room enters into pressure region. So the whole room is dominated by pressure below this point. And no amount of treatment is needed because there's no bouncing. It's just pressure change, see? So below this frequency, it's quite linear, though you do not have what we call room gain. Room gain is modal support, which is modes. These guys are your friends. They're not your enemies, but you have to get them lined up like good little soldiers, Okay, troops, parade formation. Anyway, so
one of the things that one of the things you have to be concerned about here is how do you treat the room? As long as you have modes, you can treat it with both velocity and pressure.
Yes.
Okay. But as soon as you go below that point, you only have pressure functions.
Yes.
So therefore, the velocity material has no effect on any of it.
Correct. Yes,
Okay.
indeed.
So that's really where we talk about things like diaphragmatic absorbers instead of things like fiberglass and stuff like that. So when you get below that point, you can no longer use those other tools.
Right.
You can only use that one tool that's available to you. Actually, there's two tools that are available to you at that point in time, and one is a diaphragmatic action, and the other is like the tuning of a tube, like a organ tube or something like this. Okay, so those are the only two ways you can really treat the room at that point in time. Yeah. Just resonators, basically.
Presence.
All right. Yep.
So this room is, now we've got it figured out. It's not bad. It passes Oscar Bonello's criteria. You can see blue is higher than reds or level. And the distribution, you see the points here are all pretty evenly spaced. So it's not a bad room at all. It's little, but this will do. And anyway, that's what we do first, is we figure out a good dimension. Once you have these dimensions set, you can be pretty sure that when you treat it, it's just going to be right. You don't have any resonances that you're going to have to deal with. If you try to treat a room with resonance issues, it's like trying to tune an organ pipe by stuffing rags in it. It just doesn't work. You don't tune your trumpet by, damping it or anything like that. You change the length of the pipe. So that's what we do. We change the length of the room, or the height of the room, or the width of the room, and that fixes it in physics right there.
So would I be right in saying that once I get my room ratios right, the amount of acoustic treatment that I need reduces in a room, or is
really.
non-existent kind of?
No.
There's always going to be acoustic treatments in the room.
Acoustic treatment is for acoustic control. You want to control the space. You want to control what sound does in that room. Now, you can go into a room that is solid concrete or really fresh, thick drywall everywhere, painted and polished, and it's an echo chamber. I mean, it doesn't have a reverberation time more than a second, but it'll feel like that. And it'll be hard to understand a conversation in there, even though it's a small room, because it's too everything everywhere all at once. So you have to control it. When you sit down to listen to music or watch a movie, whatever, you need to be able to locate, what the producer had placed in the program material, where the horse rides in from the right and passes to the left. You're going to hear it doing that. If somebody walks in or opens a door over here, you're going to hear that. You go looking at the left side of the screen, waiting for them to come in. See, that's the idea. But if the room is all echoey, you're not going to hear. You're not going to get location at all. If you're listening to music.
Yeah, Mars, you asked a question much earlier, and that was the size of the room calculation. Is this finished room or not finished room? And what this is whatever is bounding this room in a non-movable way. So you can have treatments on the inside, all kinds of stuff, but you finally eventually get to the walls that don't move. That's what that is describing. Okay, so that is going to describe the space at which the sound rattles around inside and doesn't move any of the boundaries of any kind. And that's all that's for. Now you will treat on top of that, so you'll maybe make this room smaller physically with different treatments and stuff, but that doesn't mean that the sound doesn't get through those treatments back to these boundaries. So this is like when we build an anechoic chamber, we put wedges inside of it. But what counts is where the walls are that hold those wedges. Okay, so it's just kind of the same thing.
Yes.
Okay.
Okay. So we call it the hard boundary, or the hard walls, the finished interior, finished partitions. Floor, ceiling. Oh, and if you add, after you calculate your room, you decide, okay, I want to put this pad treatment, and then I want to put laminated or a hardwood flooring in there, and you end up raising it about an inch and a half. It's going to change your modal calculations. So be aware of that. You need to add all this stuff in when you do your measurements, okay? Do the calculations. And the way I design any room, whether it's home theater or recording studio, I go inside out. So I put in the dimensions in, and then I build it out according to what layers of whatever we're putting on, what kind of flooring we're putting on, what kind of slab or whatever is there, or it's going to be upstairs, it's going to be a floating floor, whatever. It's designed from inside out. And we apply the appropriate soundproofing necessary for that. But it's finished to that. Now, one thing that I do add to studios, thanks to Ron, studios and home theaters, is a curved rear wall that'll break up the pressure wavefront from the speakers. You can have some powerful wavefronts coming in a studio and in a theater. So if you break it up, you don't have these various nulls going on all throughout the room, because you do have some, but not near as many. And if you're a professional mastering or mixing engineer, it will break it up to enough that null that is usually heard at the mix position from that, due to the flat back wall reflection, is like minimized or gone. So that's a marvelous thing. In a room, when you're playing speakers, you're going to have a resonance happening from front to back. It's going to slosh back and forth. I mean, take 50 hertz. Even if you have a decay of 0.4 seconds, how many times will 50 hertz bounce back and forth through that room in 0.4 seconds? It's quite a few. There's quite a few before it can be attenuated enough by the treatment you put in. See? So if you break it up on that back wall bounce, it breaks up every time it hits. That's really assisting a lot. Let me get into this one thing where people talk about 100% absorption. One absorption coefficient 1 equals 100%. Sorry, that's bullshit. Okay. Don't.
Do you really want to go there, John?
Yeah, I do. Yeah, I do. I gotta. Because I gotta.
Ron, I saw you holding your head when he said
Uh, yeah, in fact, Ron and John, there was an interesting discussion also on a forum, on a Facebook forum, which I came across, the same topic about absorption coefficient of 1. And I think it's a good time to take this topic up and thrash it down completely.
It's simple. As Ron's explained before, it's a coefficient. It's a coefficient. You take that and multiply it times the area, and you get a saving, and that's the amount of absorption that gives. But you're never going to get more than about 10 decibels per surface contact.
Okay. I'm sorry, guys. John, I'm sorry. I have to jump in here. Okay, I really got
please.
to. Okay.
Please.
I know this is your part of it. I want to stay out of it as much as I can, but I got.
I want you. I want you to.
Because this is, we were having discussion with a couple of people about this, and number one, you have to understand, the coefficient was invented by Paul Sabin, not Wallace Sabin. Okay, Wallace is the guy who discovered absorption officially. Okay, Paul is his nephew.
You mentioned
Paul,
last time, I remember you mentioned last time.
Right, he's the guy who founded Riverbank Labs. And when he presented this at the ASA meeting in 1927, one of his compatriots basically said he was an idiot. and the reason he said he was an idiot was because he deliberately made this as a coefficient. A coefficient is a mathematical construct. It basically says all the answers will fall between 0 and 1. Well, that fell apart immediately in 1927 on the first material they tested. And it was fiberglass about 6 inches thick, and they had a coefficient that came back at 1.05. So it was kind of like, how can this happen if it's a coefficient? It can happen because the mathematical construct is incorrect.
Right.
Okay. You got to understand, we're only talking 3 terms here. We're talking about the total amount of Sabins. We're talking about the total area, and then it ends up, you divide one by the other, and you end up with the absorption coefficient. Okay.
Right.
And if you end up with something above 1, that means that the bottom sector, the divider, is incorrect.
Right.
If it were correct, it would be under 1. Right. So the assumption is, what's wrong with the bottom part? And that's where the thing is falling apart every single time, because that's where we get into this edge effect function.
No.
So basically, yeah. And so the idea here is, what else affects the absorption? Not only the area, but the edges, the shape of it, there's all kinds of different things that affect it. There was this concept that area will overpower all this. Well, in fact, what we find is things like the shape of it, the edge sizes, the sharpness of the edges actually equals more than the area.
Okay.
Yes. So this is
Ron, would we be right in saying that when you say more than the area, more than the projected surface area, would that be the right terminology? So
yeah,
if you're saying, if you're talking about the sound wave hitting that surface, the perpendicular area which is exposed, we can call it the projected area. And so that area is probably less compared to what is actually to be considered. Is that the right?
Yeah, what we found here in the original papers I did in 2009, we found that if you measure one area and use the same area in a different configuration, you can have completely different answers. Yes. Okay, and that's because what happens is there is a physical area, and then as we discovered later on over the years, in fact, we're getting ready to present some papers here this year. You have a physical area, and then you have
an area which is chosen for the mathematical formula.
Yes, and it is a projected area.
Yes, and both are different actually. Like we don't have a real formula which is accurate in that sense.
Well, no, actually, that's part of what our new papers are about. We do have a formula now. Okay,
right. So it's still work in progress, as you say, as you speak.
Yeah, it's wavelength based. So each frequency has a different area that shows up.
Got it.
And we now know how to calculate that. We know how to do that. as part of today's concern, I'm going to show you some graphs to show you that we've pretty much got a handle on it now.
Ron, I'm sorry to interrupt once again. So, are you essentially considering some kind of an integral function which summarizes the various
Yes.
wavelengths? Okay.
Yeah,
So
that's exactly it.
I got the gist. Fair enough. Go
Okay.
ahead.
I'm glad you do, because I'm not a calculus person. Okay,
No,
I
I
never
have that
educated
background.
that
So
area.
yeah, I got the gist. Please go
Yeah,
ahead,
I'll
please.
show. I'll show you the formula here shortly. You can look at it. It works very, very nicely. Okay, but it does it does assume some things. But the facts are, yeah, the facts are that what we discovered is that you have to look at a whole bunch of stuff besides, and so therefore the coefficient really should not be a coefficient, because
So,
as soon as you say, I'm sorry. So if you have a coefficient and your coefficient calculation comes out to 1.2. Most of the programs like Ease and Cat Acoustic and Odeon always cut it back to 0.999.
Right.
Okay. So if you take the amount of total absorption divided by the area, you come up with 1.05 or 1.5 or whatever. And then you go back the other way. And if you restrict it to 0.99, you will never get back to the original amount of absorption. That's mathematical. That's a mathematical problem. Okay. It just,
So essentially, Ron, what if I have understood it correctly? You are basically not restricting to calling the term as a coefficient, and you're changing the basis of the mathematical formula that we are trying to construct, and you're trying to devise a kind of a new kind of a formula to calculate what absorption is. Is that correct in some way?
Yeah. Basically, the coefficient isn't a coefficient. It's a constant.
It's a constant. It's a constant which
That's all
will
it
vary from case to case. It would vary depending on the material and depending on the shape of the absorption and
Right.
things like that.
Yeah.
Okay,
So basically, by doing it a constant, you can have any number. Where in a coefficient, you're restricted to what numbers you have.
Correct. And
so it's just a matter
so essentially, what's happening is that the current the current softwares that we have are trying to restrict the value to within one. So there is an inherent error in the calculation given by those softwares.
That's exactly it. That's what we've been thinking for 100 years.
Got it.
Okay. So when we figured out what was going on, we got attacked for attacking Wallace Sabin, and we're sitting there going, we're not attacking Wallace Sabin. We're just telling you that Paul Sabin was incorrect. That's all. So but you'd be surprised how many enemies you can earn by doing that.
That's a fundamental way physics works. You create whatever you call so-called enemies, but that's how physics progresses in reality.
One thing that happens is people don't realize that physics doesn't give a fart what you think.
Absolutely.
Okay. So it's one of these things where we've been having to deal with it. And like I say, during this meeting, we'll go over some of these things to show you what's going on, because there are better ways of doing it now, and it's starting to take effect in our business. But if you're overcoming 100 years of knowledge, it is very difficult to get people out there to understand these changes, because they don't want to.
True.
Number one, because they have learned something new. They don't want to do that. It's like we're already past that point.
Right.
So I think the key behind here is, what is it? So number one, coefficient or constant is an exponential number.
Okay.
Okay.
It's a log.
Right. It's a log. It changes in this case of like an earthquake. When you go from 0 to 10, you go 10 times more. You go to 0 to 20, you go to 100 times more, 10 times 10. And same way. When you go with percentages, that's a linear scale. Linear scales will never describe exponential functions.
Never.
Okay, so this is one reason why this 100% is extremely difficult to deal with, because it was never intended to be 100% absorption. John had it right. If it was actually 100% absorption, if you had a one absorption material in a room, you would walk in the room and there would be no sound.
Mm-hmm.
Okay. Anytime you can walk into a room, even inside of an anechoic chamber, there's sound. Okay. And one of the arguments we were having on Facebook today and yesterday, and day before that, was anechoic chambers have an absorption coefficient of 1. Therefore, they absorb all the sound inside the chamber. And I'm looking at it going,
Does it work that way?
interesting. Let's see.
Interesting concept. We've never experienced. So.
Yeah, we're gonna make sound go away. And I'm looking at it going, you do know that anechoic doesn't make sound go away. All it does is it stops reflections. That's all it's intended to do. And that's done not by the material of the wedges, but by the shape of the wedges.
Ron,
Yeah,
I'm sorry. Ron, I would like you to direct your attention to the last comment on the chat window. If you can maybe just address that point. So Fennel basically makes a point of direct sound versus reflected sound. So, and he says that even if that's
100% everything.
Yeah, right. Direct sound is nothing that is not reflected sound. It's still sound.
Exactly.
Okay, there's no difference between them. Okay, that has nothing to do with it. In this situation, 100% absorption would absorb all the sound, including the direct sound. That's just how it functions. But that's not what this stuff does. And the way we know this is because in our measuring of our diffusion, one of the processes we do is we direct some sound from a source to the reflector or to the diffuser. And in order to know what is happening at the surface of the diffuser, okay, we put a flat surface there, and then we put a microphone right on the flat surface with a ground plane function, and we measure the level of the sound, the magnitude. We measure the frequency response and the phase response at that point. So we know what the sound is impinging upon that surface. Right. Now, let's drop a piece of absorption in there instead.
Right.
Okay, we know what the impinging is, and we can measure the first order reflection coming off of it at all these different angles. Okay, in that distance of, in our case, 4 meters, there's 2 things of absorption. There is the absorption of the material itself, and there's the absorption of the air between the surface and the microphone. We can take out the air absorption by knowing what the air absorption is. That's calculatable. We know what that is for each frequency. So we can take that out. What's left is the loss of the attenuation of sound from the material itself. And what we can do is take the original measurement we did, the flat surface measurement, and we can normalize it. Now, I don't know how many people in here understand what the word normalize is. But what normalize is we take an inverse of the frequency response, magnitude response, and phase response, and we put it in till we end up with 0. So at all the frequencies, we end up with 0 level, 0 phase, etc. Okay, and we start at that point saying at the top surface of this absorber, we now have 0. So any reflections that come off that surface are measured in the way of attenuation because we know it cannot equal the level at that surface. It's a physical impossibility to come off of it. Okay, so we know that. So anything that comes off, we have a negative power. So now we can describe a directivity balloon that describes each angle and how much loss there is. Okay, and we know in this situation, if you have an absorptive coefficient or absorptive material that is, quote, 1, we can measure what the attenuation is off that surface to any space in space based upon the attenuation losses. And what we know is that the amount of attenuation coming off a material that has a 1 is about 10 dB. We've measured it over and over and over and over again. And I'm sorry, people, it may not make your idea of what the 100% absorption is or anything else, but it's a fact. It's measurable. We can actually go through and say, here's how much attenuation there is off this surface. Is 10 dB of attenuation. It never exceeds that, no matter whether you would do 12 inches thick, 16 inches thick, 8 inches thick, or whatever. As long as the coefficient, quote, is above 1 or 1, that is the maximum you're going to get, ever. So that means that every time you have a surface that's 1, and you hit it with a sound, it's going to attenuate it by 10 dB. Okay, and that's it. That's all it's going to do. So now some of that sound will get through the surface to the hard surface behind it, reflect back out through, and continue on to the next surface, and do another 10 dB. And you'll do that over and over until you lose the sound. But that's not how anechoic chambers work. You know, that's what a quiet room is like, but that's not an anechoic chamber. An anechoic chamber has to have wedges that the two angles. Okay, look at your surface that you're looking at, a flat surface. And
Here, Ron, I'm gonna share my screen, and
okay.
I've got the AutoCAD up here. I'm gonna share screen while you talk. There
we go. Okay,
can,
yeah, that's good.
We can pin this. Maybe I can go ahead and talk.
Yeah, I'm going to put it on my view here as a speaker only, and now you can see these angles over the whole screen. Okay, and what's happening here is if you tab go to the back here where the square is, okay, and then take a vertical line, and by the way, you're moving your line around, so just line it up with one of the points, John.
Okay, here, I can just put a line
there
here.
You go. Okay, so that
line,
right, that's the line now at that point in time that is perpendicular to the surface we're reflecting off of. Okay, the total angle of this triangle on either side of the line
is 15 degrees left and right, so it's a total of 30.
Yeah, 30 degrees. So the point is, it doesn't really matter as long as that total angle does not exceed 90 degrees.
Right.
60.
Right.
Okay,
60,
so
right.
so if you have in this case it's 30 degrees here, it doesn't matter. The two triangles together right here, okay, the tip, equal less than 90 degrees. Therefore, if you use Snell's law and the sound comes in on a straight, like you got one of these lines here, and you hit the side wall. John, there you go, right there. Put that line in there. Okay.
I'm going to zoom out, and I'm going to put a line in. Just start right here and just go straight up. Okay, so this line comes out.
Right. So if you measure the angle between the tip and the angle coming in, that is the angle of instance. Okay. That means that whatever reflection comes off will come off equal the other direction. So if you take that angle and you come out the other way, like that way, okay, it will come off at 10 degrees or whatever that angle is. Okay, 15 degrees in this situation. So it goes off, and look at where it goes. It goes back into the other wedge.
So essentially, the sound is trapped within the wedge itself.
That's exactly it. So what happens is every angle on because of the angle of under 90 degrees, the sound will always reflect back into the wedges, into the base of the wedges, and
so it's a trap. In a way, it's a trap.
Yeah, that's exactly what it is, and the sound will just rattle around until it disappears by air absorption.
Right.
Okay, and that's how it happens. Nothing comes out of it. Now, people say, well, you can't have a reverberant field in an anechoic chamber. That's not true. You can have a field of sound, but it has no reflections, and that's what the idea here is. So, and the idea is you're trying to reproduce a free field where if you take sound, it will decay by the inverse square. That's what you're trying to duplicate. If you have any kind of reflections, the reflections will cause a difference in that. And that's why we always tell people you can have anechoic chambers that are not anechoic wedges, like not fiberglass wedges, because people say, well, you have to have the absorption of what? That's not true. We have wedges like this made out of stainless steel,
right?
And they're used underwater for sonar work.
Right.
You know, if you put fiberglass underwater, I'm sorry, it'll soak up water and it won't work very well. Okay. But so the idea is, how do you prevent the reflections from coming out? It has nothing to do with what the material is that you're made of. What it has to do with
geometry.
Geometry only. Yeah.
Geometry.
So
shape.
So that's what we're talking about when we talk about absorption of the situation. So
Ron, one more thing. So one more point. So I would like to draw your attention to the last comment. Fennell goes on to say that the angle of incidence is important when calculating absorption. So in line with what you are saying right now with regards to the new formulation that you're coming up with, would it really matter? Because I think you would be considering some kind of integral function. See, when we talk about absorption, obviously we are talking about I would believe broadband absorption or very narrow band, because like if you're
Doesn't
talking
matter.
about a broad, doesn't matter, right?
No,
So
no,
is there any,
so
yeah,
yeah, let me kind of get to where you're going to, because for 100 years now, people have been looking at this edge effect thing and trying to marry random incidence absorption to normal incidence absorption in a impedance tube.
Mhm.
So in an impedance tube, you have sound that is normal to the surface, going rattling around inside and decay. Okay,
Mhm.
and then in a reverb room like ours, we have sound coming from every angle. Okay,
Right.
and doing. You can never marry the two together.
Yes.
That has been proven 120 years now of research. It can't be done. They're completely different, because in one area, you're only looking at the absorption of one angle of incidence. And
Yes.
Fennell's right in this respect. Angle of incidence is important. Okay, the question is it important?
angle?
Yeah, and the question is it important in an overall field?
Yes, it's a
If you
field.
want to, yeah, if you want to know all the details, yes, it's important. But when you're looking inside of a room, you have random incidents of sound.
Yes.
Okay, and therefore
This is
you
the
have to
same-
integrate it.
Yeah, it's
integrate
the
those
same.
all the
It's the
angles.
same thing as trying to compare a reverberation room measurement and an impedance tube measurement. You
Yeah.
can't marry them. This is
Yeah.
what we're talking about.
Yeah, and that's the key here. Is angle of incidence is important if you want to know that it's a nice thing to know scientifically. But when you get into a room, it all goes away.
Yes.
Okay, so that's why random incidence is a much better way of doing this, because now you like you say, we have to put all these
Integral.
together. You got an integral for all the different angles.
Yeah.
And that's why that's much more important.
It's definitely more scientific. It's definitely capturing all the random stochastic
yeah,
waves that you have. Yeah.
yeah, and this also occurs to our measurements of diffusion as well.
Yes.
Okay, even though you can measure it, it doesn't mean that the results are usable.
Right.
And that's something I want to make very, very clear, is because if the energy coming off a surface is so small compared to the energy in the room, then it doesn't make any difference. It may be there, you may be able to measure it from a scientific point of view, but the question is, does it affect what you're listening to? And that's no. So when we talk about angle of incidence for like diffusion, when we measure, we've discovered that if you measure with the source between 0 and 15 degrees of the perpendicular, then that gives you a level that is adequate to be heard.
Right.
When you reach things like 45-degree incidents or 80-degree grazing incidents and stuff, the energy coming off surfaces are so small that they're 40 and 50 dB down.
Right.
Okay.
Right.
Can we measure it? Sure.
Sure, you can measure.
And you hear it? No.
Yeah. And that's the key. Can you hear it? So we have the same thing with absorption as well. So
Ron,
you have to.
Yeah, I get it. As a follow-up question, we were talking about the usage of an integral function. So would it be a double integral wherein you're on one side you're taking the frequency band, and on one side the angle of incidence? So let's say you have a double integral. Is it a double integral?
Yes.
Okay, I got it right. Good. I think I'm on the right track. So I think with that said, I would also like to direct your attention to one more question, which Fennell again asks. So the question is, how much weightage or importance would you give to the FSI? FSI is a frequency index, or basically spacing index, while designing. And
that actually is part of what our paper is. This formula it's spent the last 2 years now. We figured out how to do it for a single monolithic piece of material.
Right.
So you can describe a circular or a square or a rectangle, and we can tell you what the absorption is of that. And it took us a year to figure that out, year and a half. Okay. But then we found out that when you actually measure things and you break them up into pieces, that you can space them apart. And as long as the space is equal to or less than the size of the sample, you have an effect as well.
Right.
So you increase the absorption based upon square. So if you have a 2-foot square sample and you space it anywhere from 0 to 2 feet apart in all directions, you will increase the absorption, even though that you don't increase the area of it. But As soon as you reach 2 foot, that effect goes away.
Right.
Okay, so we had to
It
come up with a
doesn't all
formula to calculate.
disappear. Am I correct in saying it doesn't all disappear? It just lessens and lessens. You
No.
have this.
No, it
it
disappears
disappears
after.
completely.
Yes,
Very interesting.
it maximizes, and that's it. It never gets any more.
Oh, it
So it
doesn't
goes
get
up
any
to a
more. Yeah,
Right.
exactly. What I mean, it's there
Yeah.
around the pieces, but it's not in the empty space that you separated past that point. Yeah, I get
the empty space can never equal more than the size of the sample. Ever.
right. Yes.
Okay, so that's another integral that has to be taken into account. Okay.
Ron, one more question. So essentially, what you guys are trying to do is you are trying to move away from the ray tracing model and get into a kind of a FEA, or let's say a fluid structure interaction kind of a model. Is that right?
Well, it's both, really.
Yeah, it's
you know, it's Ron's doing ongoing research, and this is like we're studying this, and we're trying to match up
the point of
reality
my question is
with the math.
I get
you
that.
know,
True.
Yeah,
So-
yeah. Look, the facts are, sound has always been a fluid thing.
Right.
We always talk, if we want to compare things in physics, you compare sound to fluid dynamics.
Yes.
You know, and that's the thing most people don't understand is it's fluid
Yes.
dynamics. And if you don't meet the same criteria as fluid dynamics, then you're going to end up with the wrong answers. And part of this has to do with what they call scattering.
Right.
Scattering was decided as being a way of compensating for not knowing what absorption is. Okay, that's the best way I can put it. And it was a situation where nobody knew exactly how to calculate real absorption. So when you look at all these programs, they would always under calculate the absorption of a room, always.
Right.
So how did we fix that? We invented something called scattering. And if you look at how it's used in the programs, you'll find that the function is exactly the same as the absorption coefficient, except that they've added a quote Lambert scattering effect. Okay, which is supposed to be an explanation of why you lose that much energy. Which is, I'm sorry, it's a bunch of BS. Okay, just that simple. So basically, what scattering is now is the edge effect. That is the edge effect. So if you measure the edge effect correctly, you don't need scattering anymore. Now you have the true absorption. And now we've figured out how to do that. We actually found that the models actually match up very closely with the real life.
Right.
You know, so that's been the whole idea being here. So yeah, we need to look at sound as a three-dimensional thing.
Yes.
Okay. And one of the things that, especially in our design work, and John knows this now, is that it's not so much diffusion as much as phase change that affects what we hear.
Right. Right.
And that's not really something you can measure physically, where you can put out something out there and say, well, because the change of the attenuation balloon, we hear differently.
Right.
We hear differently because we can change the phase. And you have two different ears, and two different ears, the phase arrives at different times in your ears. And the people who are involved in bioacoustics will tell you that the brain interprets that as space.
Right.
So the more variation you have in phase between the two ears, the more spacious the room will sound. And people in bioacoustics have known this for years. Our problem is that people in acoustics have never thought about this, because guess what? The rest of physics doesn't exist for us. You know?
Yeah.
Yeah. So as soon as we start discovering that the rest of physics has an effect on what we do, then we have to start to thinking, oh, wow, acoustics is much more complicated than we thought it was. You know, so all of a sudden it becomes, you know, the domain of people that are scientists rather than just practitioners.
So, Ron, are you solving some kind of Navier-Stokes equations in that sense in the CFD domain, the fluid dynamics domain?
Yes, we are. That's part of what we're doing here. Yeah,
Awesome.
we're trying to apply fluid dynamics to this thing. so that
Okay,
it
that's-
actually figures out what's going on. And in doing our research, we've discovered that there is a fourth domain of absorption, which nobody ever had discovered previously.
Okay.
Okay. You have absorption that's frictional,
Mhm.
which is described by having fiberglass in the wall or whatever, and the sound goes through the fiberglass and it goes around all the little threads of the fiberglass, and in changing direction, it loses
Something
energy.
like this. Something like this. The fibers. This is fiber.
Yeah.
The fibers.
Yeah. So the sound goes through it, and in going through it, it slows down.
Right.
It has to change direction. It has to slow down. Sound doesn't just go through like laser. Okay.
Right.
It's slowing
Right.
down. It changes to heat.
Dissipation, heat dissipation. Right.
Right.
Mhm.
So that is absorption, by the way, just so you understand.
Yes.
If you take it all down to the last little thing,
Yes.
absorption is a conversion of energy to heat. That's it.
Yes.
That's all it is.
Yes. Yes.
Okay. So you have frictional absorption there. Then the secondary absorption you have is diaphragmatic absorption. And people think that moving these surfaces in and out like this is absorbing the sound because it's acting like a shock absorber. That is not true. You're only moving the diaphragm. That's all you're doing. What's happening is, if you look at the edge of a diaphragm where it's solidified to something hard, you're bending it. So this is like taking a piece of metal and bending it back and forth like this.
Gets hot.
Okay. And it gets hot right there where the joint is. So that's what's happening on these diaphragmatic absorbers, is they're edge controlled and they move in and out. So the edge right around the edge gets hot from the bending action. And that's a conversion of energy into heat. Therefore, it's absorptive. Now,
Well, Ron,
third
one-
way.
Oh, sorry.
Yeah.
Sorry.
Go
Would then, instead of using fibrous materials like polyfill and glass wool, wouldn't steel wools or metal wools be better at this conversion of energy to heat? And
No,
dissipation of the heat?
the heat of a frictional it doesn't care what the material is. It really does not.
Yes.
It's just a matter of how many times you make the sound change direction internally.
If I can just add one more point to what Mazban mentioned. So there is also something known as microscopic absorption, which is something that
Yeah.
physically, yeah. So that is something that you require a highly fibrous material for that to really function. So
Yeah. Sintered carbon, sintered
Yeah.
steel. I mean, there's a million different ways of describing this stuff.
Right.
If you look at open cell foam,
Yes,
same thing, the idea.
open pore.
Yeah.
Right.
So I mean, the whole idea here is to change the direction of sound. That's all you're trying to do.
Yes.
Okay.
Yes.
So now we've covered both diaphragm and frictional. There's a third, and that is resonance.
Resonance based. Yeah.
So if you have a tube and you have air trapped in it, and you activate one end of it, it'll go back and forth inside of the tube. And every time it goes to one end, it's closed, it'll compress the air and it'll decompress on the way out and recompress the other end. Goes back and forth like a shock absorber. And every time as soon as you put together the air and you compress it, in compressing it, you make the molecules go together. They become more solid, and what's the word I'm thinking about here?
Heat of compression?
Yeah, it's when you compress the air, you convert to heat. Because in this situation, you have all these molecules get pushed together. They don't like that.
That's boiling.
Okay. So they resist. You have air resistance. And the resistance slows down the sound wave. And
So
when it
basically,
slows
Ron,
it down,
you're talking about the basic concept of a Helmholtz resonator.
yeah, or a shock absorber.
Yeah.
It's plain shock absorber. So
Right.
you slow down the speed of sound. In doing
Right.
so, you convert it to heat.
Or a Schroeder diffuser with wells.
Well, we'll get into that
We'll
later
get there.
on. We,
Yeah, we'll get
we
there.
don't want to get there yet.
That's opening
Okay.
a can of worms.
Yes,
so,
I know.
so th-
I tend to do that.
Yeah, those are the three methods of absorption that we have used for 100 years now.
Right.
But in our research, because of the edge effect, we've also discovered a fourth form of absorption that's called diffraction.
Hmm.
And this occurred back in 1960 at Ohio State University, when they were discovering what happens with radar waves going over and changing direction over an edge. So they had wedges that were like so, and the radar was going like this. And what happened was it would change direction. And in doing so, the edge of the wedge would turn red hot. Yeah, it would heat up and turn red hot. So somebody said, well, it's because they're metal wedges. Because the radar waves, we're talking, by the way, in order to be able to measure this, we had to have a source that was 35 megawatts. Okay. Oh. So that's why I'm saying you have to understand that it's a matter of scale here.
Didn't
So we had 30.
Grumman use that during the development of the stealth fighter? Similar?
Yes.
Yes,
Yes,
That's exactly
absolutely.
it. That's how it works.
So
That's how it all works.
That's
yeah,
all.
absolutely. Yeah. All your fighter jets which are there, so they are basically having they are immune to the radar. So they are radar cross section. There is a term in defense which is called RCS, the radar cross section, and Ron would know that better than most. So the radar cross section is something that radar cross section is extremely small. Extremely small.
We'll give you an idea. The radar cross section of a F-16 fighter is roughly around about 2 meters, I think it is. F-16.
Yeah, it's probably even smaller than that. It's even smaller than that.
Yeah, but the point is now an F-22 has a radar cross section of somewhere around a third of a square inch.
Yes,
smaller than
it's so small.
Smaller
it can't
than
be spotted. It can't be spotted by, like, for all practical purposes. It's immune to a radar.
Yeah. So it's about the size of a bumblebee, basically. Okay,
And,
so that's how it works, and we also have absorption materials on it too.
Yes, the radar absorption materials. Yes.
Right, and that's highly secret, and that's why nobody knows this stuff. So, so back to our situation with the diffraction. So we know that when it goes over, so what we did is we changed the wedges from metal to wood, and when we did the same thing, the edge of the thing burst into flame.
Oh,
wow.
And it was like, well, I guess it has nothing to do with metal. Okay, it burst into flame. So somebody said, well, let's try it with fiberglass. So we did it with fiberglass too, and the edge melted. So the next concept is, if it has nothing to do with metal, what's happening? Well, what was happening is every time you bend the radar wave, the action of bending, it changes the phase. If you change the phase, you have a loss of heat along that edge in the air. And if you have heat conversion, what do you have? Absorption. Okay.
Right.
So what we discovered is, by the act of changing the direction of the sound, you have the absorptive function along that edge. Now in sound, it's very small. You can't even measure it hardly at all. But when you put it together with a whole bunch of edges, now it becomes significant. Okay.
Right.
And this is why when we measure absorption, you want to have the smallest ratio of edge length to area that you can get. So what is the smallest circumference available around an area?
The perimeter.
Yeah. What is the perimeter? What is the length of the perimeter? What is the shortest one you can have around an area that surrounds an area? Matt. A circle. That's the minimum you can have.
Correct. That's right.
Okay. Okay. So if you measure a circle, it will give you a certain amount of absorption. You calculate it using the method. And if you take that same area and convert it to a square, you'll get a different measurement. And what this came about because of the measuring process of scattering, where you have a circle sample. So we measured the absorption, and then we took the same area and made it into a square, and the square gave us about a 20% higher absorption.
Right.
And we're going, okay, that's not supposed to happen, because it's supposed to be, area divided by, or absorption, which is exactly the same, okay, divided by a thing. So we said, well, what happens if we change it to say a 4:3 ratio, like a rectangle, and it went up another 10%.
Okay.
And then we went to an 8:2 sample, and it went up another 15%. And then we broke it up into 2x2 pieces and put it on the floor and just scattered them around the floor. So we had the maximum amount of perimeter to area available.
Right.
And in doing so, we increased the absorption coefficient at 1K in this particular material, which is a 1-inch fiberglass, from 0.88 to 1.7.
Wow.
Oh yeah, that's what I'm saying. The amount was like almost double.
Wow.
And somebody said, well, that's impossible. Well, okay. So how do we prove that the edges are effective? Well, this is simple. You take away the material.
Right. Right.
and leave the edges. Now, how do you do
Right.
that? It's like we make edges in imagination and put them out in space and measure them. No. Okay.
Right.
But what you can do is make a 2x2 sample made out of steel.
Right. Right.
Okay. Now you take these 2x2 samples, the same amount you had with the absorption.
Stack them up. Stack them up.
No, no,
Well, you
no.
don't stack it, just scatter it around the floor. It's like you
Scatter
do the
around
other
it,
stuff,
yeah.
right?
Right.
And you measure it. Do you get any
Right.
absorption? Okay.
Right.
You know darn well the material is not going to give you absorption. So
Right.
anything you measure has to be tied directly to the edges. And we measured it. And the average coefficient of absorption of steel scattered around the floor was 0.2.
Huh.
Okay. Now think about that for a second. You can now make an absorber to go on the wall made out of steel. Put it on the wall, and it will still give you an absorption of 0.2
Hmm.
at all the frequencies.
Hmm.
Now, this is like, ooh, we can get absorption doing nothing.
Right.
Okay. And this, when we presented this, you want to talk about controversial? Oh
Right.
my God, you couldn't believe that people that scream bloody murder. It's like you can't have absorption, but you have no material. Well,
Right.
well, you want to argue with the measurements? The guys that were there for the measurements were people who were very well known in the industry. Ken Roy from Armstrong, a number of other people like him. They were there as part of it, and they all said the same thing: if we had not been here physically to watch all this, we wouldn't believe this.
Right.
So,
If I have to summarize what you're saying, Ron, just for the benefit of everyone, the moment you introduce an edge, you would have some amount of absorption inherently, irrespective of the material that you're using.
yes. So now let's talk about why that's the case.
Right.
Okay. If you have a point in space
Right.
and you have a ray hitting it and it changes direction, it will
Right.
change direction in any of 360 degrees.
Omnidirectional.
Yeah, completely omnidirectional, right? So
Right.
that is a change in energy for that ray.
Right.
Now, if you take that point and extend it in one direction, you now have
Right.
an edge.
Right.
Okay.
Correct.
So now the energy is coming in along that edge. And the way
Yes.
physics works is you can come in at any angle on that edge, but coming off that edge, it will always be normal to the edge.
Yes.
So if you have the edge going X, Y, or X plus X minus X, the sound will always come off in the plus Y minus Y direction.
Yes. Yes.
Okay. 90 degrees.
Yes.
So now what happens is all these points all occur from different directions coming in, but they'll all come off. And what happens
Right.
is when they come off, they are all equal phase.
Hmm.
Because if they're all in the same direction, they will have the same phase.
Yes.
Okay. So now you take this edge and extend it in the Z direction. You now have a face that is vertical. And you have the edges, and we come in on an angle, any angle, right? It comes off normal to the edge, that's first, and half of the angle of whatever the other face is.
Hmm.
So if you have a 90-degree face, it comes off at 45 degrees.
Right.
Okay. Again, they're all the same direction. Therefore, they're all in the same phase.
Same
And
phase,
therefore,
right.
and that another word for that in the same phase is coherent.
Coherent. Right.
Okay. If it's coherent, it's also additive.
Sorry, what's the term that you used?
All the
Additive.
energy, all the energy that's coming off in the same direction as coherent is also additive.
Right. Additive. Yes. It's
Right,
it's like
because-
the vectors align in the same
Some,
direction.
there's some.
Yeah.
Well,
Vectorially.
actually, what you guys are talking about is it's the same as a laser.
Yes.
Okay. So that's why lasers are so effective in energy, is because they're all coherent energy.
Directional. Extremely directional.
That's exactly it. And it's all additive. Therefore, you had heat that occurs from that. All that energy focused at one spot.
Right.
Okay. It's the same way with sound, by the way. So,
Right.
so now if you have a straight edge, you'll always have coherent energy. If you have a circular edge, it comes off normal to the edge. But each point on that circle is a different angle.
Yes.
And therefore, if it comes off normal to that edge, it will always come off following the edge of the curve. And therefore, there's a change in phase
Yes.
at each
Yes.
point.
Yes.
That means all the energy coming off a circle is non-coherent.
Yes.
And therefore, it's not additive. and therefore you don't get an additional amount. And that's why the circle gives you less absorption than any square edge item does. And therefore, now the question is, what shape should an absorber be? Well, the idea here is to make as many edges as possible.
Right.
So what is a shape that has lots of edges? A
Circle.
star shape. Well,
A star
no.
shape. Okay. Yeah. Okay.
A star shape.
I'm sorry.
Right.
A star shape. Yeah. Yeah.
Yeah, it's the opposite of a circle. So
Yeah. I'm sorry.
any kind of
I
star
meant
shape.
the other way.
Yeah.
Yeah.
So lots and lots and lots of things. So the idea is to maximize the amount of the length of the straight edges to the area. So that's what you do. So if you want to have maximum amount of energy in this situation, you want to make sure you maximize the length, the ratio of the perimeter edge to the area. And that's how you maximize your energy. So in our situation, we figured that if you take a star shape, you can increase the absorption of an area by about 3 times.
I think the best shape, there is a term in physics, or let's say mathematics, it's fractals. Basically, you're talking about a fractal shape.
There you go. There you go. You actually got it right there. And that's the whole point, is this is going to force people to start looking at absorbers in a 3-dimensional way.
Right.
Okay.
Right.
So now you're going to have absorbers that have, all these other edges around in a XY type domain, but now you're going to have to increase that in the Z domain as well.
Right. Right.
So now you're going to have these absorbers that look like a star.
Right.
A 3-dimensional star in all directions,
or
a sea urchin,
Right.
But Ron, is there any limiting factor as to how close one edge should be from another, or how close it should not be?
Yes, we talked about that earlier. Whatever the area is should never exceed the space in between. Or the space between should not exceed.
But that is at the maximum point. But what about minimum? How close can edges be?
Well, they can be right next to each other.
So then what if you had like a row of like baffles straight up, like a comb kind of arrangement in a comb?
That's what we've been testing.
That's what we've been testing. That has been around for years. Okay. The first tests that were done in the 1920s were done that way. Okay. So you can look at all of that. But basically what happens is the space in between can never exceed the size of the comb teeth.
So
that's a straightforward geometric construct. I think
that's exactly it.
Yeah.
So if you look at all the old data that's been around, there was what they call strip data. They would make a piece of absorption that was 3 inches wide by 16 feet long, and they put another one right next to it, 3 inches away, and 3 inches away, and 3 inches away, and they would get huge amounts of absorption.
Right.
So that goes back to the old measurements, the old research papers from the 1930s, and that's. But nobody ever bothered to pursue how to actually calculate that. They just noticed that it showed a difference. That's all. And then they went on trying to marry it with the impedance tube measurements. So it's not that this wasn't explored many years. It's just nobody ever bothered to pursue it to the point of using it.
Right.
But Ron, so there's also the question that arises as to wavelengths, right? So, I mean, if you consider geometrical shapes, then, I mean, are you then tying down the ends in forms of frequency? Like, I mean,
yes, yeah,
of course.
And would they be limited by quarter wavelength physics, or what?
And that's what that spacing is. The spacing is dependent upon the wavelengths.
So essentially, Marsban, if I have to, Ron, I'm sorry to interrupt. So essentially, we talked about something like a fractal concept, a fractal geometry. So if you're talking about, let's say, a lower wavelength, you'll just have a larger size fractal as opposed to a smaller size fractal.
Right.
Am I right?
But the
spacing is going to depend on the frequency.
Right? So if you have like an equal spacing, you'd only absorb one frequency, is what I'm trying to say.
So if you have a large fractal, that will take care of all the frequencies above that.
Yeah.
Am I right?
Yeah. What happens here is whatever size you start out with, you limit the low frequency and everything
Right.
above it is fine.
Absolutely.
Everything above it works great. So,
Right.
so what you do is you decide where the lowest frequency is that you want to deal
Correct.
with. You
Correct.
create the unit that way, and then everything above that is okay.
But Ron, so let's take an example where I'm trying to absorb, say, 80 hertz or 100 hertz or something, and I need to space them, say, 3 feet apart. And I've got 4 feet panels, which are spaced 3 feet apart. Now, at this spacing of 3 feet or 2 feet or whatever the space in between, if I have a 16 kilohertz wave, that's going to reflect off that spacing. It will not get absorbed by those absorbers at that particular point, right? Because there's no edge.
No, that's not true. It depends on what the material is. If you have fibrous material, it's going to suck up 16K.
No, at the material would, but when you've got the spacing is
It-
a plain
it-
wall,
it-
right? That's going to be
it-
a reflector for 16 kilohertz, right?
No, it's not in this situation because remember I told you, it becomes an apparent material.
Ah,
So it has the same characteristics as the material does.
Oh, okay.
Oh yeah. So that's why it gets really interesting. So yeah,
It's
it will absorb.
counterintuitive.
Yeah, it has to do with the fact that it's an apparent material. Okay, so whatever the characteristics are of the material, it will carry over into space.
Even if that material is plain concrete wall, right?
Yeah. It
Yeah.
hides it.
It's like a ghost.
Oh, okay.
Yeah. Yeah.
Okay, and that's why it's scary because you have to start thinking now into what the geometry is. So
Right.
if you want 100 hertz, the first thing you have to do is figure out what size panel will see at 100 hertz. Okay, well, if you think about that for a second, then you got approximately 1 foot for 1K. That means 2 foot for 500 hertz. It means 4 feet for 250. That means 8 foot for 125. So it'll be somewhere around 10 foot.
Right.
Right.
This means
Right.
if the panel's not at least 10 foot,
Right.
it's not going to see 100 hertz.
Right.
Okay, and this is why there's been this misnomer for years about material thickness and how much space you have behind it. Okay, so if you have a 4-inch material, people are saying, well, you can raise it up to 4 inches off the surface and increase low frequency absorption. That is untrue. That's the best way I can put it.
Yeah.
Okay. So, and here's why. It has to do with fluid dynamics again. Okay.
Yes.
So if you have a fiberglass panel that is 4 inches thick, the sound will go through it and out the other side.
Right.
Okay. Now, if you have a gap behind it, there is now an area or a volume that is pressurized by the waveform.
Right.
Okay. If the gap around the outside edge is small enough to prevent all that air from moving fluidly through there without any pressure, back pressure, then it will not do anything. So as you decrease this space, you decrease the edges, the exposed edges, and therefore you have less volume being able to leave under the pressure. And therefore, if it can't leave, it'll build a pressure inside of it. It's apparent pressure again, as long as that edge is small enough to keep it at least partially contained. And you'll get some. Yeah, so it's got to be 1 inch or less. Anything over 1 inch, the apparent size of the gap is large enough to allow the pressure to relieve to zero. Therefore, there's no effect. Okay, so as long as you have an open edge, 1 inch is the limit. And we've shown this over and over in measurements. Now, if you take that edge and you close it off like an E400 mount or an E mount, where you have an edge that goes all the way to the surface and blocks that area in, now that is a trapped air thing, like a resonance area. And as long as you have trapped air, you have an effect like a shock absorber, and you have increased low frequency absorption. If you have 5 or 6 inches or whatever, okay.
Yeah,
That's
you're
always trapped
using
air.
two of the absorption techniques. You're using the fiber and the pistonic.
Right. Yeah. So I mean that's what you have to realize is if you leave these things open, fluid dynamics works. If you press water and you have a big enough drain, the water goes away.
Right.
Okay? This is one of my examples I use for teaching about reverberant rooms or reverberant energy. is think of a room like a bathtub.
Right.
Okay. You have a 1-inch drain and I have a 2-inch source. Okay. Water comes in at twice the volume that the drain will allow to go out, but it's still a drain. So the question is, will the bathtub fill up?
Yeah. If it's a 2-inch source and a 1-inch drain, the bathtub would fill up.
At what point? At what point does the fill stop? It will not overflow. You honestly think it will overflow?
Yes, it would.
Okay. No, it won't. And here's why. Because as the volume of the water goes up in the bathtub, the pressure of the drain
okay.
and the
It's
pressure
called relief.
compensates.
It's called relief. It's called pressure relief.
Okay.
Yeah. So you know what I'm saying, Kartik?
Yeah, I know.
At some point, the water will stabilize at some level in the
Right.
bathtub, right?
Right.
Okay. That pressure, that level is the reverberant field in a room. Okay.
These concepts are also used. These concepts are also used in hydraulics and pneumatics, basically in designing the pressure relief valves and all those
Yeah.
things.
And these are also used in aerospace for airplanes and all kinds of things. So it's funny how physics applies everywhere. Okay?
Absolutely.
So in this situation, I always ask people, well, why is it that you could take a SPL meter and go out in the room and say, isn't this great how even the sound is in the room? Okay. They'll take an SPL meter out there and they'll go out beyond where the speakers are and say, yeah, see, it's the same level everywhere. So this is great absorption in this room. This room is well treated and everything else. And I will look at him and go, okay, think about the fact that you are a person laying down in this bathtub. Okay. And your nose is the probe. Okay. If you are above the water level, you are in the direct field of the speaker. Therefore, as you lower yourself, you go away from the source, you'll actually detect the difference in the pressure, okay, by breathing. Now, let's say you lower your nose to just below the surface of the water. I mean, we're like a 1/4 inch below the surface of the water. When you breathe, what are you breathing?
Water.
Breathing water. You're water, right? Okay. Are you going to drown?
Probably if you breathe in too much water.
There you go. Now, let's say you lower your nose 1 foot below the water. Are you going to breathe water?
Yeah.
Same.
Are you going to drown?
Yeah.
Same.
Okay.
Yeah.
Therefore, the result is you have the same level of death,
Same
which
level
is what which is the measuring that you're doing. It's the same SPL. The result is the same. So no matter where you are under the water, you are equally dead.
But rather than that, I think the better analogy would be the effect on your eardrums as you go from with your nose just at the surface and go 10 feet and go 10 feet. What's the pressure on your eardrum?
Sure, but my question to you is this: do you care if you're dead? So, the real point here is I'm just trying to demonstrate that when you get out beyond the critical distance, the sound level in a room will be the same no matter where you are because you're equally underwater. Okay.
Absolutely.
So when you have people out there with a Radio Shack sound level meter say, isn't this great how even all the sound is? I'm sitting there going, well, yeah, if you don't mind being dead.
Yeah.
Okay.
You're in the.
So
It's a fundamentally wrong measurement. It's a
Yeah.
fundamentally wrong measurement, and
Yeah.
you get excited by a wrong measurement, and you say that okay, I'm measuring the right thing.
Right. Well, and you just brought up something, Kartik, that really bugs me all the time. People say, well, we did a measurement. I don't care if you did a measurement. If you did a wrong measurement, it doesn't care. It's still a
Absolutely.
wrong measurement.
Absolutely.
Okay. You can measure anything. Doesn't mean you have a good measurement.
Absolutely. That's exactly
so-
the point.
Yeah. So when people come back and they say to me, well, I put something in a room and I measured it and it took something out of the room and there's a difference. Well, that's nice, except for one small problem.
You
Do
don't
you
know
know
what
what was do you know what was in the room before you put the thing in? Okay. And the other question is, if you're measuring it, do you also subtract the absorption of the air where the sound is traveling through?
Right.
No, I just measure the difference. I know what the difference is. So therefore, that's how much absorption it has. Well, no, you don't know what the air is absorbed between that source and your ear. So if you don't take that out, that means whatever you measured is not correct. And that's what all these standards are for, is to tell you how to do this. And that is, if you have a reverberant room, we measure this level, empty room, the full room, and then we take out all the air absorption in the thing. And because it's a diffuse room, we know what that characteristic is. And we subtract all that. We take out all the other things because you make sure the room doesn't have an absorption coefficient of its own that is above 0.01. Okay,
right.
so
that right there is critical. That right
so,
there is extremely critical. And
so
why
if you
you
measure in a room like
test these things.
Yeah, this is why a room like cardiac, I see in your background, you have all these things hanging on the wall. Okay, what is the absorption characteristics of all the couch, chairs, and everything else in your body? Okay, that's the point. If you're out there measuring it, you can't measure it with your body because your body is absorbing.
Exactly.
That's why you have to put a microphone in and walk out of the room, seal it up, make sure the air is not moving anymore. You have to make sure there's diffuse field and stuff in order to be able to measure it.
In fact, the very microphone itself would have its own geometry, which would add to the absorption.
Yeah. I mean, it's just, and you have to, you have to take that.
You're talking about literally probably a omnidirectional small microphone, which is the size of a
quarter inch. So people think that just putting the material in and measuring it compared to a room tells you what the absorption is, and all it tells you is what the end result is of doing something, but you don't know exactly what you did.
Right.
Okay. And that's why we have these standards, and we use rooms like reverb rooms, which are controlled environments where we know what the absorption of that room is to the nth degree.
Right.
And now we can subtract that room out, and then we can also take out all the air. And it's not just oxygen. We have to know what the losses of energy are going through oxygen, nitrogen, carbon dioxide, all that. So we know how much there is at each frequency, how much loss there is per foot traveled of sound going through air. And we have to back that all out. We have to back out all these other things, all these compensations. What is the compensation for a concrete floor on a room? It has a certain amount of absorption.
Right. So, Ron, you have raised a very important or very interesting point. So, effectively, what we have been assuming for time for many, many decades is fundamentally a flawed kind of a concept. So, what is if I have to ask you, I'm just trying to articulate this question. What is the extent of error that we have been assuming so far? To what extent we have been off the target? Because when you say that you're getting coefficients, or let's say I won't use the word coefficients, I'll use the word constants, like as opposed to what we assume as point, let's say 8, you're getting 1.7. So that's like way off
more than double. It's like, I mean, it's
I did a paper. You go to my website, you can download it in San Francisco on how to measure a unknown piece of material. Okay. And in there we took the material, measured it the standard way, came up with a set of absorption coefficients. Okay. Numbers, constants. We also did the measurement where you split things up, so we can calculate what the perimeter ratio
edge absorption is.
Right. We calculated that, and then we put in a piece of material that had a shape that I had no idea what it was. The guys did it for me. We measured it, and then they told me what the shape was, so I could calculate what it should be. And the calculation was somewhere in between the two. Okay, which tells us we still didn't have all of the space. That's when we didn't know anything about spacing at that point in time. So I published those papers, and if you'll go in there, you'll see at certain frequencies. And by the way, this effect only occurs at certain frequencies. So if you have 1-inch material, you get the maximum effect at around 1200 hertz. Okay, and it goes down on either end. So the maximum change is around 1200. Now, if you have 2-inch material, it's around 600. And if you have 4-inch material, it's around 300. What does that tell you? Every time you change the thickness of the material, you lower the Q, or you lower the frequency of the Q by half of the frequency.
Right.
Which means you can predict what's going to happen with 6-inch or 8-inch or 10-inch.
Yes. Yes.
because it's going to move downward. Okay, that's one of the things that's been discovered is we can actually predict what's going on here a little bit.
Right. Right.
But what it did tell us was this: we how do I say this? God, I'm trying real hard not to sound stupid here. You can, oh God, John, help. I remember where we were with this thing, and I got off in this other angle here.
Yeah, we're talking about the percentage of error that is.
Oh yes, thank you.
found.
Okay, so when I tabulated all this stuff, we found that the predicted, the difference between the predicted using the standard absorption and our prediction and the actual measurements was 85% error.
Wow.
85% error.
Yeah, that was like,
What
are you kidding?
So effectively speaking,
All
the
rooms
formulas,
designed till now are wrong.
the formulas that we're considering are fundamentally absolutely flawed, and they are completely out of place. If 85%, you don't consider 85% as a something that which is within the bounds of acceptable limits at all. So
But we've been doing that for 100 years.
Right. Right.
And we're getting by. It's not
Yeah, we're
bad,
getting by.
but
Yeah,
it can be way better. We can do so much better.
Well,
You know.
okay. Now, here's the difference between a consultant who is purely science-based and a consultant who uses experience. Okay, so if you have people like Leo Brandt, and he'll tell you, well, if you have this in an audience area, you should probably, just as a general rule, increase the area or the volume by 10%. Now, why? Because in reality, when we actually measure the rooms, you needed that extra 10% to come up with the actual revert time. Okay, so what's happened is there's a whole bunch of guys out there that were called golden ears for years. Leo Brandt's one of them. Okay, there's a number of other people like that. What they've learned over experience for years is that you take what numbers there are, and by experience, you increase them by certain percentages in order to come up with an answer that actually makes sense. Well, when we actually measure these things in the way we're doing now, we find out that the amount of absorption increases by just about that much based upon the edges. And that's what we're doing now, is we're now converting these measurements to a usable number that can be used by scientific people who don't have golden ears and be able to figure this out. And this is called magic sauce.
I think I would also like to say that probably the application of physics, I've just written that on the chat window also, like application of physics to acoustics, I think is a more contemporary kind of application, because and especially the study of acoustics in a more like a fluid dynamics approach. I think that's something that has been done very recently. Of course, you have more and more research being done, but I think the traditional approach of considering it as a pure wave, or let's say a ray tracing approach, is fundamentally flawed.
But
Okay.
it's flawed when you're dealing with the wave end or the bottom end. And the thing is that designers doing home theaters or studios are too focused on the ray region. Yeah. And I've always said this: if you get 20 hertz to 350 hertz right. You got your you're good to go. You're good to go. Yeah.
Yeah,
absolutely.
And that's the key is we do everything based upon light analysis.
Right.
Okay. And that's all dependent upon frequency. And when you get below a certain frequency, it falls apart.
It's exactly the same reason that we say that at low frequencies we tend to be more omnidirectional, and whereas in the case of higher frequencies we try to be more directional. So that's exactly the point. And Norman makes a very good point. Ray acoustics is very easy. Absolutely correct. I think the moment you talk about multi-dimensional things, you're talking about integral functions and more complicated calculus involved, and which makes matters difficult for a lot of people.
Everybody just wants to do it the easy way.
Let me make something here, a little thing to think about here. When I first started this process, I had been hearing from Leo and other people about how NIST here local, that would have been the National Institute of Science
Science and
Technology.
Yeah.
Right, and that was originally another name previously, the National something other council or whatever it was. It was for standards, NSC, something like that. The point here is this is the government agency that is supposedly to take all the science, put it in one spot, and do the research. And they would pay for all that. And there was the very first anechoic chamber was built for Bell Labs by Leo Brandt. Right, and they built it for the NIST. Okay, they also built reverb rooms for the NIST. At one time, the NIST had the largest anechoic chamber in the world. It was like 120 feet by 120 feet. It was huge. Okay, so I called the NIST in 2009 when I first started talking about the edge effect thing. And I got this guy answered the phone, and he was a nuclear physicist. And I said, "Can you pass me on to the acoustics people?" Well, we don't have any acoustics people here. I says, "It's part of physics. What happened?" "Oh, well, we tore the anechoic chamber down a few years ago, and we tore down the reverb chambers a number of years ago because, it was a settled field back in the 1800s. We don't need to discover anything more because there's nothing more. The basic knowledge of acoustics is there."
Oh dear.
Yeah, and we discovered all the basics. So all the rest of this is just trimmings on it. And I'm looking at it going, really?
How wrong could we? How wrong could they be?
Yeah.
I'm going to comment on somebody commented about changes and what we're discussing now and the discoveries that we have now, is that science is only ever beaten by better science. And
Yes.
this is how we do it. We stack it. It's never like we'll never discover that, all of this is wrong but it's this. No, we'll just add to it. We just stack on it and it'll go this direction or this direction. And that's fine. But that's what we want. We just want to get.
Yeah. Norm is right. Science evolves. But it also evolves based upon the fact you have better tools.
Right.
Okay. And the reason we're getting all this stuff that you're getting now is because of the facility we have. Okay. The average reverb room in the world is around 200 to 210 cubic meters. Okay. If you look at the cubic meters and calculate the Schrader integrals, it rolls over and dies at around 160 to 200 hertz. This means that anytime you measure anything that is lower in frequency than 160 to 200, you're making the best. Yeah, you're making the best guess is all you're doing.
Yeah, it's a I would say a very poor guess.
Yeah, but it's a guess. The point is if you look at all the data that's been published for the last 100 years, it all goes, we can measure all the way down to 80 hertz. No, you can't. You can measure to 160 to 200 hertz, and then you make a best guess after that. So all this data that we've had for absorption has been really restricted to around 200 hertz. It
is extrapolation based on what we have.
Yeah, and a lot of times the extrapolation is wrong.
Yeah, it's wrong. It's fundamentally wrong.
So what's happened is I got asked 25 years ago to open a laboratory, and I couldn't figure out how to make a better laboratory. So why duplicate what already is out there? So I waited and I waited and I waited and I waited and I waited. And I finally decided that I was going to open a laboratory. And in doing so, I wanted to have the largest reverberation rooms available in the world for this particular service. Now, there are other reverb rooms that are much larger, but they're not used for this project, this type of measuring. So ours is 737 cubic meters.
Whoa, holy.
Yeah, it's a big room. Okay. In doing so, because of its size, we have 5 overlapping modes at 20 hertz, which means we can measure 20 hertz as accurately as anybody else can measure 200 hertz.
Right.
And what you're seeing now is the results of what we're doing. We're showing now the low frequency things that are going on, and we can reproduce those over and over and over again with repeatability of better than 95%.
Wow.
So Norm brought up something a little while ago. John, you have it, I think. That's 7064.
Yeah. Let me show you that.
Can you put that graph up?
Yes, I can. Let me find my folder.
These are things that you understand. John has been spending enormous amounts of money to measure these quote normal materials we use for design, for recording studios and listening rooms and stuff. And one of the things that's been out there, and John has been propagating as well as a whole bunch of other people, is that 706 is the most popular material out there. It's a Owens Corning 706 6-pound density. That it can't do low frequencies. It's too hard. It reflects low frequencies. Okay. And again, John has been really good about this, and take my word for it. I can tell you that eating crow is not like chicken. Okay?
No, it's not.
I've had to go back and apologize to 200 or 300 students over the years about things I taught 10 years ago because it was wrong. Now, did I know it at the time? No, I taught at the time what was available out there. Now I know better. So I had to go back and call all my friends up and say, guys, what I taught you is bullshit. Okay. So here's what's happening. Well, John has been doing the same thing. And one of these things is 706. Okay.
Right.
706. Yeah, it's scary what we found. It really is.
Here, I'm going to show you. I'm going to show you right here. Okay. So this is 4 inches. Just 4 inches. Now,
wow.
You do a quarter wave calculation. Do a quarter wave calculation. Now, 4 inches thick of fiber. What are you going to get? You're going to get not much.
Yeah, not much.
Okay.
Right. Wow.
But this is the real test. And we did we also did 6 inches, and it didn't really improve very much.
No. And 2 inches rolled off at about 100 hertz, 120 hertz, something like that.
So I on a slightly lighter note, I would like to just point out, John and Ron, please change the y-axis to absorption constant and remove the word coefficient.
Well, eventually we will.
As soon as we get the standards people to agree to that.
Yes.
No, I don't think any standards committee need to agree about that. Coefficient always is going to be less than 1, so there is no question of anyone agreeing to that. It's a fundamental. It's a fundamental.
Well,
yeah.
Now I do have to caution people that this is very wide. Okay, it's all the way down to 80 hertz. Okay, and it's very even all the way across. So if you judge materials, you can judge them 2 different ways: effectiveness and balance. This is a very well balanced material.
Very well balanced. Yeah.
Okay. Effectiveness, there's other materials that are more effective. They have higher absorption coefficients that are up in like 1.1, 1.2 and stuff like that. But they're only at very special place. Like 703 has that big bulge at around 80 hertz that goes up about 20 dB louder. But it's only at that one point. It actually rolls off at the higher end. So we have those measurements too, and we have materials like PET and all kinds of stuff. So
here's pink stuff.
Yeah.
Here's the pink stuff, pink fluffy. This is 8 inches thick. We get way up there in the low frequency region here. Wow. Really nice. All the way down to 70 hertz.
Wow.
Yep.
An easy 70 hertz there.
And this is the stuff you buy at Home Depot or Lowe's or someplace like that. It's called Owens Corning Pink. That's what it's called. It's called Pink. Okay.
What would be the primary material composition? Norman, if you could maybe chip in? Fiberglass.
It's fiberglass.
Yeah. It's the same stuff you put in your walls for insulation of your ceiling. It's
used basically for heat insulation, I suppose.
Heat insulation.
Yes. Yeah, and if you look at it by the R number, this is R13, R15, and R30. Okay, so that's 3 inches thick, 6 inches thick, and 12 inches thick. Okay, and that's what we measured along the way. And this is all the same density. It's around 2.4 pounds per square for cubic foot.
Wow!
So it's very light. This is the stuff you go down and buy, in bales.
Now I just want this is off the topic of acoustics, but aren't these materials generally let's say fire hazard, potential fire hazard, or not really?
No, these are fiberglass.
Glass doesn't burn.
Glass is made from sand, Fiberglass is made
Yeah.
from sand.
Okay.
Rock is made from basalt rock. Neither
right.
of
So,
them burn.
of course.
Now,
Right. But
I-
what about let's say okay, fair enough. I take my I get the point. Right. Fair
Yeah.
enough.
Yeah.
Yeah, no, they're fireproof. They're considered fireproof materials.
Now I have
Right.
I've seen tests that fiberglass does tend to ball up a little bit when it gets very hot.
Well,
Okay.
it's glass.
Because the glass is really thin and it'll heat up quick and just kind of ball up like when you're burning your hair. But it doesn't burn, it just melts.
Actually,
Okay?
I'm sorry. I raised the wrong question. What I meant to ask was from the point of view of health hazards, because a lot of people talk about potential health.
Carcinogenic. Yeah.
Carcinogenic, yeah, they're known to be having some health hazards.
Well-
That's one of the reasons why a lot of people are slightly hesitant in using glass wool and stuff like that. So yeah,
Yeah,
your take on that?
It's the particle size that gets inside your lungs. It's the same as asbestos, stuff like that. Okay. In that respect, yes, you put a film on the front of this stuff that it can be either
Acoustically transparent,
scrim, like a scrim.
yeah, fabric.
What I use in all my treatment designs, I put a thin layer of, 1/4 inch of Dacron or polyester batting. They use it for filters, and you just put it on there, and then you put your fabric over it. And the Dacron or the polyester is usually nice and white, so it just shows the color of the fabric. And if you have this rock wool or the rigid fiberglass or whatever, the pink stuff, it's pink. You don't want that showing through. So you put the Dacron there, it protects from fiber egress and
Right.
Yeah,
because
there's
think
ways
Norman
of
is
changing it.
Very true. Norman, I think, addresses that point. So there is a perception in the market. I might be wrong completely that Norman has addressed it, saying that there's no report of like any kind of health hazard.
The thing is, this is what I've always said, and I don't know. You mentioned like asbestos, Ron. It's not. It's
No, it's but I'm talking about the fiber size.
Yeah, fiber size. It's an irritant. Wear a mask. I don't know. If you're not wearing a mask, what is like the comedian damn, what's his name? Says, what is wrong with you? If you're not wearing a mask, okay.
Think about
You're
when you're installing it. I mean, you wear a mask, you wear a coverall to make sure that the glass doesn't touch your skin, because it's glass. It will cut you. Okay.
Right.
It will cut you. And if it gets in your lungs, it will lodge in your lungs as fibers, and it won't dissolve. It doesn't dissolve. So therefore it will cause it'll cause injury.
But that's the least of the worries. Okay. The problem I think that people are having with these products is the binding agents that are used to assemble them.
Right.
And you need to let them air out. That's the problem usually.
Absolutely.
My whole family, I'm not allergic to anything. I could probably eat rocks and I'm fine. But I'm serious. But my wife and children, they have asthma and they have allergies and histamine reactions to almost everything. So, damn. But I got rock wool panels, which I don't like. I like much less than glass wool, because rock wool here at least is crumbly and leaves a powder residue sometimes, and that turns to dust and it causes allergies and whatnot. But it's the binder system in this stuff that's horrible. And
I think the binder is the key, because that's what is going to decide the porosity and all those aspects.
It's the VOCs.
Yep.
So let it air out. Just let it air out. Put it in the garage. Open it up. Let it air out first, and then you're good. Leave it for a week.
Yes. Fennel asked, have we tested ceramic wool? Yes. We've tested ceramic wool. We've checked rock wool. We've checked fiberglass. We've checked all kinds of things.
I think.
And again, John is right. It has to do with binder.
I'm due for sending my samples too in that case.
Seriously, you should. You really should. I'm eager to find out how that works out.
Well, one of the things interesting is, John, you should probably pull up the 4-inch or 6-inch PET.
Oh yeah. This stuff
So
is
this is supposedly the stuff that's supposed to help you get rid of fiberglass and rock wool, and it's made out of polyester, and it binds together. It's woven together rather than just bound together, so there's no binders in it.
It's kind of like made like a felt, like
Yeah,
like
it's under
make-
pressure. Yeah.
Okay, I got here's 4
Is
inch.
it compressed polyfill?
It's
Yes.
kind of, but it's yeah. So this is 4 inches thick. Now look, I want you to notice something here. What the heck is this? It's over 0.9 at 40 hertz. And this is only 4 inches thick.
Yeah, and let me point out something to you. That same peak is the 2 inches and 6 inches.
It's almost like a notch filter.
Yeah.
It has to do with how this stuff is constructed. Okay, this stuff is compressed like felt. So what happens is if you look at the material, if you look at this stuff.
Yeah, here's the 2 inch. There it is too. See? So 2, 4, and 6. Look at 6 drops down to again 70 hertz here, very effectively.
Yeah.
And then from about 42 to 28.
Ron, could these be the effects of maybe some microscopic absorption?
No, what this is again the situation when you do fiberglass or rock wool or anything else, you use a binder to hold together the particles.
Right.
In PET, it's done by compression. So what happens is you have a variable density going from the outside to the inside, back out to the outside. So it gets more dense towards the center and less dense towards the outside because of the way it's made. And what you're seeing there is a resonance in the density as the sound goes through it. Okay. So so it's a different material and it reacts differently because of the variable density.
So we have just recently come up with another option of a material composition, so which is exactly like a replacement for PET. So we have come to that with a formulation based on wood fibers. So so
I hate to tell you, but Kartik, you may not be happy about hearing this, but we've had material here that I'm trying to remember what the name of it is made out of wood fibers held together by concrete.
No, the binding out here is not concrete. It's a natural binder. So I'll share the details with you on an email, and we'll take that forward.
Around here in the United States, we had something that was bound together with cement, but the point is it was made out of wood fibers, and it was different thicknesses, and it worked very, very well.
This is not wood wool, Johnny. This is a slightly different concept. Wood wool, in fact, the one which I showed you earlier is like a replacement for wood wool. This is made out of coconut coir. So this actually the image won't do justice to what you're seeing, because this is a very, very fine, there's a lot of fibrous material inbuilt. It's compressed coconut coir. So
that would be interesting to test.
That would be interesting.
Yes, exactly. You got to send that. Really? Yeah,
I will.
Yeah. And Fennel said it's going to be expensive to get it tested. It's just as expensive for you as it is for John. you can calculate that for every absorptive test you do, it's going to be around $1,000.
I'll just take a few questions. I'll just ask a few. I'll just maybe direct your attention to a few questions posed on the chat window. So Johnny asked a question. How about width of the tested sample? Does that affect the low frequency absorption? I think of course.
It doesn't affect it. It doesn't affect it as much as depth does.
Yes, depth. Johnny, you want to unmute yourself and just maybe articulate that question, because I think, Fennel, I'll come to the phase grading question too. Johnny, would you mind unmuting yourself and maybe asking that question from your side?
Yes, hi. Basically, I was asking when you were talking about the absorption coefficient of the fiberglass, the dense one, So I wanted to know if widths will affect the absorption, the amount of absorption on the lowest frequency, because we are talking about only 4-inch and we're getting a lot of absorption on 80 hertz, let's say. So if, let's say, the width of the sample will be smaller, will we have the same absorption on the
Yes,
lower,
yes,
on these
yeah.
frequencies?
Yeah, it's per area, okay, per square
Well,
foot.
you have to, the area is the key here, but you also have to look at the perimeter.
Yes,
And,
the
and
perimeter,
a narrow,
the perimeter.
a different narrow would be narrower. You'd lose a little dimension at the top and bottom, but the height's the same. There is very little difference between the two. So the determining factor on absorption in this situation is always the thickness. Okay. The other things have some effect, but not nearly as much as the thickness does.
So basically, it boils down to saying that if I have a monolithic material, or let's say a monolithic kind of a construction, it would not depend too much on the. It would only largely depend on the depth. But if I have, let's say, multiple, let's say, structures, then of course the perimeter comes into picture, wherein you have multiple multiple edges.
That's right.
And multiple edges which are coming into picture.
Right.
Karthik,
And there,
Karthik,
there
can
the
I come
thing-
in here?
Yeah, Sunil, go on.
Yeah, so this surface area, the square foot coverage of surface area, will it affect only the amplitude or only the frequency or both?
It affects mostly the frequency. Okay, so in this situation, like I said earlier, when we measured 1-inch material, fiberglass, it peaked at around 1200. Okay, the effect. If you had it with 2 inches thick, it peaked at 600. And if you had 4 inches thick, it peaked at 300.
No,
So
Ron, I'm not talking about the depth, I'm talking about the surface area.
the surface area in this situation was the same for all these.
But say if you have the same material, say a 2-inch thick material, and one sample is a 4 square feet sample and the other sample is a 16 square feet sample,
They will be different. They will be different.
Yeah.
Obviously,
in
that's
the
quite
amplitude,
obvious, isn't it?
in
Isn't
the
that quite
amplitude,
obvious?
not the no, but in the amplitude, not the frequency, right?
No, you'll have some amplitude differences as well. Okay, because in this situation you have probably absorption coefficients that exceed 1 in most cases.
Okay, thanks for that.
Okay, so yeah,
okay,
that will change the amount of absorption.
Exactly, yeah. So the
Okay.
amount of absorption is the frequency
Right.
affected will not change, but the amount of absorption will.
Yeah, well, here's the thing to keep in mind. The frequency will change when you change the
Depth.
apparent
Depth.
the apparent configuration. So if you have a sample that is a square sample that is 6 by 6, 8 by 8, 10 by 10, there is a difference in the amount of absorption, but the peak and the frequency ranges will be the same.
Okay,
Because they're determined by the configuration, which is a square.
I get it. Okay, yeah.
And we get
So,
to point
so
of-
basically, just to put that in perspective, you are always looking for given a particular surface area that you have, you're always looking to construct the largest perimeter kind of a geometry. So the answer to that is basically a fractal kind of a construction. So that's going to give you the best kind of a.
Yeah, and you know that scientifically that's right. Now the question is, can you actually put a fractal on a wall and make people go? That really looks nice.
So there is a practical limit to that. So that's what you. So you increase the number of edges. So simple answer to that, as you said, is the
simple answer is
star option. The star option.
Simple answer is a checkerboard pattern.
Yeah, absolutely, absolutely.
Yeah, and not
That's-
the standard one. The standard one goes corner to corner.
Mm-hmm.
Which you want to make sure you have that much space all the way around, which means you have let's say you have a 2-foot checkerboard pattern in it. You have 2 foot of space all the way around that 2-foot piece, and then you put the next piece in. So
Right.
it's a very open pattern. I can show you some examples of that if you're interested, where we actually have done that with a number of facilities here, and it looks very attractive. People like it, and it's like, yeah.
Please
but-
do show us some examples. We get a better idea of the understanding.
Yeah, please.
What's interesting here is this is something that Leo Baranek was pushing way back in the 1940s. He always said that checkerboard patterns work much better than a solid piece of absorption. So when you have a room and you put these big 4 foot by 8 foot panels up, you can actually get 3 to 4 times as much absorption by breaking it into 2 by 2 pieces and just scattering around the surface.
Absolutely. Makes a lot of sense. Makes a lot of sense.
So
I do a lot of ceilings like that. If
yeah,
I'm not putting it, if I'm not putting a drop ceiling in, I'll put I'll do that on the ceilings.
Yeah.
Tracking spaces and stuff like that. It's great.
One more question, Ron. Just one more question. So, Fenil, would you want to ask your phase grating question from your own side, please?
Yes. So the simple question is, what are your experiences with phase grating elements in an acoustic space?
Let's talk about that.
Quick.
Anybody familiar with something called the BAD panel? If you're familiar with RPG,
Yeah, a BAD panel. Yeah, a bad panel. Yes, yes.
They're
yes.
talking
Yeah.
about Michael Jackson's bad, right?
binary, binary,
Binary. Yeah, RPG bad panels. Yeah.
Okay, so let's talk about that, because when I first got into this business, I had to test for scattering, and we measured it for scattering and had absolutely no scattering. Okay, which went against everything that everybody was talking about. It said it was a great little panel. It did this, did that, and everything else, and it had great diffusion. Well, we measured it for diffusion. It has absolutely no diffusion of any kind. But, and here's the big but, when you looked at the frequency, or not the frequency, but the phase response, okay, from about 14K up. Let's not talk about below 14K. Let's talk about above 14K. The phase response went from a very, very coherent pattern to a very incoherent pattern, like a big sea urchin. Okay, when I presented that to people here at Applied Physics at university, the bio people said, yeah, your ears interpret that as space. And my first thought was, well, that's interesting. We've never heard that in acoustics before. And one of the girls answered, she says, yeah, that's because you guys don't discover or work with bioacoustics. You work with the architectural acoustics, and you guys never got smart enough to figure that out. So it was like, okay. So the way I try to put that is, I don't know how many of you are guitar players or use amplifiers for guitars or anything like that, but there's a company here in the United States called Fender that makes guitar amplifiers, and they all have a control at the far end called presence. Okay, now if you know anything about electronics, that's my specialty, is I'm an electronics engineer, is if you look at how it actually operates, it injects 16K hertz noise into the sound. And what does it do? It makes the sound of the guitar sound like it's in a large echoing chamber. Okay, more space, right? If you're familiar at all with boards, mixing boards, a company called Mackie, okay, produced a little dial that says air.
Yeah.
Okay, what does it do? If you turn it up, it injects 16K hertz noise into the channel, which makes the sound airier. Okay, the point is
presets.
Yeah, and well, the point is it increases the noise,
right?
And increasing the noise, by the way, also increases the phase differentials in the sound. Okay, so what's happening here is that these units, when they go into a room, and I have to tell you, I have big concrete empty rooms, lots of them. Okay, I must have 500 or 600 of them. Okay, that are 20, 30, 40 meters long sometimes. And if I go in there and measure the room impulse response, it has a certain response that it's there and you can see it. If you put these panels on the wall, you can definitely hear a difference, even though it doesn't change the impulse response very much. But you can definitely hear the room open up. And it's like, have you ever heard a really open room become even more open? It's like, oh, wow, that's cool. Okay. So what we figured out was that by changing the phase response at 14 to 16K to your ears, you experience this openness. So these bad panels do not have a diffusion characteristic, but they do have a phase grating characteristic. Okay, and by having phase gratings, you change the phase in huge amounts, and in doing so, you increase the airiness of a room, the openness of the room. It's a subjective thing that your brain hears. It's not something that is physical, but it is your brain interprets it that way.
Psychoacoustical.
Bingo. And that is the big thing people do not understand is psychoacoustics plays a huge amount in what we hear. And you
Right.
can't measure that. You can only observe it.
Right.
You know, so does the BAD panel work? Yes. Okay, it works. It doesn't work the way they say it does, but it works. Okay.
Right.
And Fennel, what you're asking about is phase grading elements in an acoustic environment. If you're going to use phase grading elements in an acoustic environment, be aware that it's not going to change the characteristics of the reflections, but it is going to change the characteristics of the room into a more open room. Okay. So you can use these panels on the wall.
I should show what we're doing, what we've been doing recently. I'm actually, let's see, where is this? I'm going to open up my AutoCAD and show something I've been working on. So, because this is related to studios and home theaters, and it's some ideas of what you can do. Just a moment. Let me get to the model. I'm going to share screen here. Yeah. Go ahead. Here, let me look at sideways. I'm going to take this stuff off the top. We're going to look down into the room. Conceptual. Come on, you can do it. Change. There we go. All right. So this is what I'll do with a lot of my rooms. Of course, you're going to put your speakers up along these lines here. If it's LCR, then it's LCR. And this is all phase grading here. Behind this, they're open in the back to bass trapping. And I've got broadband panels here. Then we got phase grading here with bass trapping behind it, broadband, bass trap, et cetera, et cetera. And this is alternates. Another thing I do around the room is I call it an indirect lighting board, but this is cut sharp edges, lots of edges here, same here. And to reduce flutter in the room, because a lot of people like to record in their control room or the mixing room, and in a home theater too. If you have enough ceiling height and you're doing Atmos, I put angled panels on the wall. This was only part of it. It angles back up and then it goes into a drop ceiling, which is more absorption. And this basically, these reflectors here, this is a reflector. It keeps the high frequency energy in the room a little longer. It doesn't kill it all off. Look at the back of the room is all phase grading with bass trapping behind it.
And there's a curve in the back wall as well.
A curved rear wall, yeah, baby.
That's what John was talking about. He was alluding to that, right? Providing a kind of a convex shape towards inside.
Yes, so it breaks up the pressure wavefront.
Yeah.
So now let me show you. Let me get back to Zoom here. I've reduced this thing in such a way that I can't find anything anymore because I'm looking at something else here. So it keeps coming up. Where the hell? How do I? There we go. Okay, there we go. Let me see if I can share my screen. Okay, I can't share my screen, guys. So somebody has to tell me I can share my screen. Okay. Sorry. Yeah,
I'll just give you the option of sharing a screen. 1 second. One moment, please. I'll make you.
I've got a black design ATEM, so it's. I don't need permission.
Right.
Okay. Let me show you. There we go. Can everybody see that?
Yeah.
Yeah.
That is a phase grading. Okay. That is the same pattern as the BAD panel. But these are made out of stainless steel. Okay. These can go over any kind of fiberglass. and the impedance change between what's in behind these holes and what's on the front is what institutes the phase function. And if you see the size of these holes, these are 2 foot by 2 foot panels.
Right.
Okay, so these small holes are all doing phase shifting like crazy at around 14 to 16K.
Right.
So this is a phase grading panel. John,
Ron, that's related to the diameter of the hole, is it not?
yes, and the sharpness of the edges of the hole.
Yes.
Yeah.
Okay, so that's why the metal ones are actually better than the standard BAD panels are, which are wood, because they have a sharper edge.
Right.
Okay. By the same token, John, let me. Would you bring up your DWGs of the 601 or 601-1?
Oh yeah, I can. Just a minute.
Yeah. Let's do the 601-1. Let's do the 601-1.
Let's see. Where is it? Oh my goodness. Just a minute. I got to find my this one. And just a minute. Getting it.
Ron, is there anything else that you would be sharing from your screen?
Yeah, there probably is, but we haven't got there yet.
No problem. I'm just asking because I'll retain you as the host till the time you want to share your screen. Okay, no problem.
Do whatever you need to do. We'll work it out. Okay,
Absolutely.
but John, I can John, if you don't have it, I can share the screen here with that same information.
The 604, you mean?
No, the 604-1.
Okay, yeah, I got it. Okay, here it is. This is the AutoCAD. Let me share. All right. So this is the
one over here on the right hand side. The one on the right hand
the right hand side. Okay, now this is just a line drawing of the top. This is the -1, and what we've done, we put the slats going. This is the front of the unit, right here. This is the front. Okay. The square is the back. This is the back of the.
So do you have the 3D drawing of this?
I did. Just a moment.
Yeah. If not, I can bring.
I gotta find it. Let's see. So vent slats test. Yeah, this is it. This is the 3D version. All right. So
there we go.
Conceptual. So we can see what it's looking like. This is our test version. We sent this off, built exactly like this.
It's 4 foot. Yes, it's 4 foot by 4 foot, and the idea here is the edges themselves are diffraction gratings. Okay, they're all in one direction, but the curve is, I think John explained to me, it was a prime 27 curve.
This one was quite a bit higher. I don't remember. I got to look it up.
Yeah, whatever it is.
I don't know.
I thought you told me it was prime 27, but
no,
but in any case.
That's the other ones. Those are prime 17. This was a 43 or something like that, something screwy.
But the point is at lower frequencies, the curve acts as a reflector. Because all these surfaces are so close together, they're all the same distance apart. And that when you get a larger wavefront, the front edges become solid all the way across. So now it reflects. So if you look at the actual GLLs, the actual balloons of these things, you can actually see that these actually reflect all the way down to about 125 hertz, quite nicely. And they're very asymmetrical. That's the other part. They're very asymmetrical. So this is part of what you have to do when you start looking at things. Is if you have a curve, you could take these things and put these on a curve. So you have a curve on a curve.
Right.
And you get really weird things happening, but it's all predictable.
Right.
And that's what the whole idea behind here, and that's what John's doing with all these things he's talking about at the front walls and stuff, is this type of thing. We use this particular set of curves on a studio that he and I designed together in Saudi Arabia. And all the walls of the performance rooms are done with these things. So they all have these curves and all these things like that. And in the place, by the way, I found out they did build it, John.
Oh yeah.
Yeah.
Oh, wow.
And they're very pleased with the sound of the rooms.
I gotta see it, man. I gotta get a hold of Hamza and find
Yeah.
out
Yeah.
what's going on
Yeah.
there. Yeah.
So in the meantime, just wanted, and then you can do the spacing. Right now, this spacing is even spacing. So you have, let's say, a 3/4 inch board, you have a 3/4 inch space between them. So they're the same spacing. But you can change these spacings to an MLS or some kind of another series, and they do provide different patterns of higher frequency diffusion. You know, so and if you fill these things with not fill them, but put a layer, say 4-inch fiberglass behind, they also do some absorption functions as well at lower frequencies. So it's these are very useful. I think John makes these in 8 by 4 foot sections, 4 foot
Right.
wide, 8 foot high
No,
to go in a room.
no, they're 8 foot. These are about 8 foot by 8 foot when they're the main ones. Here,
Oh,
I'll show
okay.
you. 604s. Where is it?
You got more of a problem than I have.
Why?
Oh, there it is. There it is. They're supposed to be like in numerical order. Okay, so
Ah.
this is 604.
Why they
This is
call
what
it
it looks like.
604s? Is it a 60 by 40 kind of diffraction?
Yeah,
pattern?
it's all about 8 by 8, but it comes in 2 sections. It's 2 pieces. This
Ah.
is the piece that we tested, basically the left side of this, or the left side facing it. And then I want to test this side too. And, you know, that way I can put both GLLs together kind of in okay, it's going to do this here and it's going to do that there. And it's going to shape the sound in this way. These are the standard 604. What we were looking at here is the 604-1, which the slats are facing, are going inside like that. So it's very interesting.
Yeah, it definitely was more effective than the 604 was.
Yeah, brilliant. Yeah.
So it's just, you know, but again, maybe we just used a whole bunch of terminology that people are not familiar with, and one of them is GLL. Okay,
Oh, okay. Yeah.
GLL is a
Speaker lab file.
yeah, it's a Speaker Lab file. Speaker Lab being a software package provided by AFMG out of Berlin, and it's used to describe what speakers do. So you can look at the directivity balloons of a speaker. Well, what is a diffuser? It's a speaker without a voice coil. Okay.
Beautifully put.
Yeah. So the idea here is if you illuminate the diffuser from outside and you then go from that point and measure just like you do a speaker, now you can get a directivity balloon of a diffuser by using the first order reflections and by isolating those. And what's happening here is in ease, you can put a GLL of a speaker in a room and it will illuminate the room using the directivity balloon exactly the way the speaker will. And therefore you can see reflections from corners and all kinds of stuff. And you know, you can tune the aiming of your speakers and how they cover and what type of speaker you use, whether it's 60 by 40 or 60 by 20 or whatever. Okay. Well, you can do the same thing with diffusers now. Now, does the software support it directly? No, you have to do a workaround. Okay, because in the program, speakers always speak at 0 time, and then it calculates from 0 time to the running time to where it hits a wall or whatever it is. Okay, so you can't have another source that speaks on its own because it's there. Okay, so but you can create this balloon that you can put on the wall, say 50 feet away. Okay, now how do you get it to speak in time? That's easy. You measure the distance between the speaker and that wall, and you calculate that in milliseconds. And then you delay it. So let's say 50 milliseconds. So the speaker speaks, 50 milliseconds later, the diffuser speaks, just like it would be if it were struck by the speaker. And now you can see what the effect of your diffuser in the room is. And the nice thing about this is if you have a single diffuser measured like a 2 by 2, you can put them together in a GLL function as a cluster, like you would a speaker. So if you had like 3 speakers put together in a cluster, you can calculate what the resultant balloon is based upon the complex addition of magnitude and phase, and have a resultant balloon of those 3 or 4 speakers. Well, you can do the same thing with diffusers as well. So you can take these diffusers, put them on a wall, And let's say you have a 6 wide and 2 high array of these diffusers. Put them together, call them a cluster, recalculate the entire overall diffusion balloon that comes off that entire array. And now you can put that on the wall. And when you speak at it, the entire rear wall will react as if it were a whole array of diffusers in these things. So now you can use your diffusers in these programs by just that simple workaround by calculating what the delay time is. So these are things that are they're what's the word I'm trying to think of? They're not patented, but they're copyrighted. There we go. Yeah, proprietary copyrights. So GLL is a proprietary method. There's other software that can read these same files that are out of Germany and stuff. So you don't have to have Speaker Lab, but for the cost of it, I'm sorry, just buy the stupid program. It's not that expensive. It's only a couple $100.
Ron, I'll just once again bring us. Let's get back to some questions that are being asked.
Sure.
So Fenil has a question, which is quite, I think, a nice question. What about a room shaping? That is walls playing, and is that a recommended practice, or is it recommended to have a simple rectangular room?
Let me answer this.
Yeah, I'm going to let John answer this one.
Okay. A rectangular cuboid is the easiest. It is the easiest thing to calculate and to be sure. You can calculate it and that's it. This is what you get. But you splay the walls and you go, there's a lot of unknown here, because when you splay walls, you do not get rid of modes. You're still going to have them, but they're going to change every centimeter or so, or every inch. It's going to change, right?
So the point being, John, that is there any benefit of splaying? I don't think so.
Not in my mind.
There are benefits to reflection situations, but
agreed.
They're offset by the problems with modal analysis.
Right. I use angled rooms and weird stuff going on in tracking spaces, and that's wonderful because it breaks things up. And a tracking space is a creative space. If you have a tracking room in a big studio, I mean, if you have a big rectangle, that's fine. You treat it properly, it's great. But you often want to do some modal analysis on it a bit. Now, in a room that has a booth built into it, and you got other stuff in it that's different shapes that will change the resonance activity within that space, then that breaks it up somewhat. You got an angled wall, that's fine. But as far as a mixing, mastering, listening, critical listening space, keep it straight, simple, and treat it properly. Yeah, keep it simple, stupid.
John, John, the room that you showed us, the console room on that studio, you had splayed both the speaker walls. Is that for soffit mounting the speakers so that they are angled?
I usually do, but I like to take advantage of area and space for trapping. And I angle my walls, the front walls, in at 25 degrees, not 30. And the reason for that, I want your speakers to be aligned with those walls, but in position. So the horizontal dispersion of a good speaker is quite wide, at least 90 degrees, if not more, quite often. Okay. And so you can be in the center without it pointing at your nose, and even pointing out here, left and right. You're still getting a really good focus. But when you get up and walk around the room and ponder, and which I used to do when I was mixing, I'd get up, pace back and forth and listen, and I'd sit back down. You should maintain your stereo image. A lot of times in some studios I work, you got the speakers sitting on the console right there, and they're pointed right at your nose. You got to sit there like this to listen to it. And as soon as you move like this, you can't hear it right. You're missing a lot. So it's evolved into a 25-degree angle, so it spreads out a little bit. You got a lot wider sound stage where you can move around, and you're not strapped in your chair with a vice on your head. You know,
Will
this,
this,
this is not Clockwork Orange. We don't make like that.
will this,
John,
will this help in home theater rooms? Playing
Yes.
front, left, and right kind of.
eh,
I don't know. I think if you get a good wide dispersion speaker, LCR flat, that's the way I would do a home theater.
Okay.
here's something to think about, and Norm can chime in on this as well. You have to determine when you're listening what type of thing you're going to listen for, okay? Because you could be in a concert hall with a orchestra, and the idea is to have the sound appear to come from everywhere. Okay, you don't want to localize it. It's like a church. If you're in a big church, like a European style church or cathedral, the idea behind the architecture in this situation was so that you would have the sound appear to come from heaven. Okay, so the organ was made, and the architecture was such that when the organ played, the sound appeared to come from above you, around you, and through you.
Mm-hmm.
It's the same way with the choir. That's why the choir was behind you rather than in front of you, was to be up high enough to be able to reflect through all these surfaces, all these various surfaces. So it sounded like the angels were singing. That was the idea. Okay, so if you want to be in a room like that or a concert hall, and you want to be in the audience, you want to be able to experience the orchestra in total rather than individual.
Mm.
So now you look for a diffuse image.
Mm.
By the same token, if you want to be in a nightclub and you have a combo in front of you with 4 or 5 pieces, you want to have imaging. So you want to know that if the organ player is playing, he's over on the left-hand side over there, and the drummer is over on the right-hand side, and the singer is in the center. Okay, so you want to have imaging. Now, imaging and the other way of experiencing sound are polar opposites. Okay, you cannot be in a room that does both equally. That doesn't exist. Okay, that's one of the reasons people who design rooms, concert halls, and clubs and stuff have to. You have completely different things going on. Okay, so you have to design the room to do what you want to do. So what you're saying is, can we have a listening room that does both? No. Okay, that's a simple answer. No, you can't have. So you have to decide what type of music or type of sound you want to have.
It's very application oriented. I'll just Penil, just 1 second, Penil. I'll just make you ask your question one moment. So essentially, if I have to summarize what Ron mentioned, these are very application specific kind of geometries that you're talking about. One geometry cannot overlap with another. Like you cannot have, let's say, an application which is talking about a concert hall kind of experience and merge that with having the same geometry replicate let's say a reproduction kind of environment. I don't think
How do you talk to a client? So you tell a client, wait a minute, if you want to going to listen to orchestral music, I got to design the room this way. If you're going to watch a big bang action, I got to design the room this way.
No,
Disco music, I'm going to design the room this way.
Ron, can I just attempt to answer that question and correct me if I'm wrong? So that is where the problem probably what you can end up using is scattering. So the acoustic treatment of the room also gives you some flexibility in trying to let's say change the what you can bring into the picture in terms of what you can offer to the client. Isn't that right?
Well, let me kind of jump in here a little bit, because Norm will tell you the same thing I will. I think he will, and that is depends on what your treatments are. So
Right.
if you want quadratic type of treatments, like quadratic scatter and stuff like that, you're going to get phase change. And when you get phase change, you're going to lose localization. Okay, so the idea here is, in order to be able to have localization, you have to maintain the phase of the originating sound. So the only way to do that is by reflecting sound in the room using a specular reflector rather than a quadratic type reflector. So now you're going to use things like barrels or pyramidals or sphericals, stuff like that, geometric type reflectors. And so you put those on the sidewall in order to maintain the phase relationship from the sound because it goes out, hits the reflector, okay, and comes off specular, which means it maintains the phase change as you move through space. If you hit a quadratic, you're going to scramble the phase completely and lose whatever localization there is. So there's two ways of doing this. One is you make a room that does one or the other. The other is a more expensive way of doing it. That is, you take the barrel diffuser and put it on one side of a rotating panel, and you put a quadratic on the other side, and you put it on the wall so you can rotate it around, and you have variable acoustics.
Variable acoustics, adaptive acoustics. Yeah. A lot of people do.
May I come in here and say
Yes.
something about this? Okay. Norm just said there are performance spaces and producing spaces. And I think some of our audience may be confused by our banter about these two things. Okay. Whereas we were supposed to be talking about like listening room, critical listening, mixing, mastering, home theater, etc. These kind of spaces should be designed well. Designed right, the target spot is larger than when poorly designed. Is what Norm said, and I agree. It should be as large as possible, and it should be. You should have a focus sound in any of these spaces. Now, in a performance place, it's different. You want to use the side polys. You want to have cross correlation. All these things that help you localize the sound on stage, and you get more enjoyment out of the performance. That's completely different than these small rooms where we're mixing, mastering, listening to just critically listening to music, or having a home theater experience. You want it pretty tight and right. Now, these diffraction units you can have past the point of reflections, and they give space to the room so that you're not in a dead room. You don't want to be in a dead room. But you can be in a very tight, acoustically tight room that sounds good and feels good to be in. It's all.
So there's a question, John, that comes up is, what's the ratio between absorption and diffraction or reflection? It's like, is it the first 1/3 which is absorption?
Really a ratio.
And no, the first 1/3 of the room is absorption, and the next.
No. We're falling back into the old live-in, dead-in criteria, which had some great ideas, but a lot of it was not really true.
No, I'm talking specifically to home theater rooms.
Home theater rooms, yeah, you don't want a live-in, dead-in, no.
Because aren't the surrounds supposed to be diffuse? You don't want to localize your surrounds, because then you're falling into the exit door effect.
How are you going to diffuse them?
By putting your diffusers and around the
that doesn't diffuse,
and using dipole surrounds, maybe.
Dipole surrounds are often nice, but put the surrounds up to where they're distant, and perhaps you can have a diffusing grid in front of them if you want to do that. I've never thought of doing that. I don't think at one time years ago, I designed a home theater where we had the surround speakers facing a diffuser, like a quadratic.
Yes.
And then that broke it up into the room. But I don't know how that worked out.
Mars, can I come in on this? Did you want to say more of a reverberant surround field than a diffuse surround field?
No, not a reverberant, but a diffuse surround.
If you don't want to diffuse, no. Basically, you do not want a diffuse field in a listening space like this, because what you want to hear. You want to be able to hear what the producer, engineers wrote into the program material that's being put to this speaker, that speaker, that speaker, this speaker, and to give you the experience that they programmed into it. Otherwise, you're like I'm adding a big reflection over here and a big one over here that wasn't in the original movie or in the original track. So you're broadening your experience. Yeah, it's nice, but it's not original. It's not what they wrote. That's what I term accurate or expansional. You can put phase grading on the left and right sides of your home theater where you get a lot of home filtering and sounds more spacious and stuff. It's changing the whole character of the sound, and it's not what was written onto the disc that you're playing.
It's not basically faithfully reproducing what was intended.
No,
so it is not.
That's exactly right.
No,
It's not.
Karthik, I have one last question before I leave.
Please.
We've been talking about all the tools that acoustic designers or acousticians have, beginning from absorption to reflection to diffusion or scattering, but we've not really touched upon redirection of sound in terms of, yeah. So we need to talk about that.
Well, and that's what we're actually discussing that right now, and that is redirection of sound. By the way, that's otherwise known as a new method of describing reflections. Okay.
Yes.
So instead of having a reflective surface, we have a redirective surface, and that's to define it from a diffractive surface. Okay. But in reality, geometrics are the only things out there that are good at redirecting sound. And now the question becomes, where do you want to redirect the sound to? Okay. If you want to do it in a horizontal method, use something like a variable diameter cylinder. Okay. So you have different radiuses, and they vary. So you have this surface looks like a drum surface of it is round. Okay, and that will reflect the sound in a horizontal direction only. The other way of doing this, and the method a lot of us use now in concert halls, is spherical surfaces. So if you take a sphere and you do a cut across the surface of it at some point, it doesn't have to be a diameter, it can be any point, and you end up with a section of a surface. You put that on the wall, and now it redirects the sound in a spherical method in all directions.
It's a convex lens.
Yes, it's a convex lens. That's exactly it. And the point is, it reflects back in all directions. Therefore, it gives you more of a. So it's one of these things where I use a lot of these up in the ceiling.
I'm gonna do.
That is a point.
Stop. I might do the
Okay,
pasta.
I have somebody.
It's gonna take so long. So, question is how to do it.
I'm not sure who's talking here.
My head hurts since yesterday.
Lud Bjorn.
Okay, if there's a question from the audience, I'm sorry, I had to mute the person. I'm sorry, I'm not able to pronounce the name. I'm sorry for that. So if there's a question from the audience, please unmute yourself and ask the question. There was also a background noise. I would request to avoid, let's say, crosstalk. So yeah, if there's a question, please unmute yourself and ask the question. The gentleman with starting with LJUD. I'm sorry, I'm not able to pronounce the name. So if there's a question from your side, is there?
Yeah, Lud Bornen.
Yeah. Okay, I don't think so.
Okay.
It probably might have been inadvertent. Yeah, by mistake. I'm sorry. So yeah.
So the point is, so we use these partial spheres in the ceiling. So we put them up in the ceiling so that the sound gets distributed across the entire area from the reflections of the ceiling area, and they're supported up there, and hanging from chains and stuff like that. They work really good, but the only reason you use these is to maintain localization. Okay, so this is part of what we're talking about. Do you want localization? Like if you're listening to a movie, you want to know where the sound is coming from in the movie. So if a person is talking to you in the movie, you don't want the sound of that person's voice coming from the right side when they're standing on the left side. It drives you crazy. You don't like it. You stop listening. It's just there's a part of your brain that goes, nope, this isn't right. Okay.
It is fatiguing. There's a lot of ear fatigue which comes into picture.
Yeah, SIPTE did a number of studies on this during the 1930s, 1940s, and they found that SIPTE would be in motion picture people. They decided that you want to make sure that your audience stays and watches a 2-hour movie. Okay, so you don't want to piss them off. They leave then, okay, and they don't spend any more money. So the idea was they figured out what the best curve was for frequency response, and they figured out that localization was very important. So that's why if you look behind the screen of the old screens, you had speakers, spaced almost all the way across the entire width of the screen. And you would send the sound that you want to that particular speaker. So if the person were talking, they would be at that speaker talking. Okay. So your eyes would go like this, and your eyes want to go where the sound comes from. So so the idea here is if you're building a room to listen to things that are spatially important. You want to make sure the room supports diffusion based upon a geometric reflector or redirector.
Ron,
So
can
Ron,
I?
that's coming back again to localization that you spoke about, right?
Yes. Yes.
Now, here's a question. I mean, we as humans have our ears, which give us an idea where sound is coming from in the front of us. Can we do the same localization when the sound originates from behind our head? Or from
Yes.
above our
Okay.
head?
Yeah, you're right in one respect, and that is our ears set up where our sound comes from. You're wrong in the fact that it's just in front. It helps in the front, yes, because our ears pointing slightly forward, but in reality, it's a horizontal area. So anything that's in the horizontal around your head, your ears pick up quite nicely and determine where they are in space.
And above your head?
Vertically and like this, it doesn't work very well. That's why you put speakers way up here, and it sounds like it's from out here. Okay, you don't your ears do not determine vertical distance very well. Okay, or vertical localization. Fennel, you keep asking questions.
Ron, in continuation with the redirection of sound, say we're talking about the ray acoustic region. Say you have a flat surface angled at a particular angle to the incident sound. Will that flat surface also redirect sound?
Of course it will.
Yeah.
Yes.
So then, so in that case, say we have flat surfaces at the first reflection points angled at a certain direction, we will be able to redirect the first reflections to some other space instead of the main listing space, right?
Yeah, you can do that, no trouble at all. That's one of the things we do all the time, is anything that you have to look at the time differential. So if the time is between 0 and 25 milliseconds, you want to keep that in your area, because that increases the intelligibility and that increases the localization. Once you go beyond 25 milliseconds, you want to make sure that reflection goes away from you, because that will introduce the effect of an echo, which now reduces localization and reduces intelligibility.
So in that case, angled walls or splayed walls can also work with a similar effect, right?
They can, but again, they have their own sets of
that's the idea behind the splayed walls. Yeah.
That's the idea behind splayed walls, right? Redirection of sound.
That's like that's going back to the old criteria of an untreated room, basically.
Exactly.
An RFC room, untreated. You don't put up treatment. Well,
keep in mind that at some point inside, you're going to get reflections from other spacings. So if you have something close by that's giving you under 20 milliseconds, a little farther back, you're going to get a reflection from behind you that is 60 milliseconds, and that's going to be a problem.
Yeah.
Okay. Yeah. So that's a disadvantage to a splayed room or a fan-shaped room, is you end up with the weird reflections from behind you that you don't expect. So, and the problem is you can't make them go away, because that reflection could be an early reflection for somebody in the back.
Right.
Okay. So that's one reason why rectangular rooms are easier to predict what's going to happen, because now you can calculate all the angles of redirection.
Yes.
Thank you, guys. I will be signing off now.
No problem, Fennel.
Karthik, Mars, everyone, thank you.
Thanks.
Take care.
Thanks.
You know, I prepared a paper with all these charts and stuff, and you can get to it.
Yes. One of the problems, Karthik, is this. This is such a complicated field.
Yes.
That we can have 2.5-hour meetings every 2 weeks for the next 6 months and still not cover the same stuff.
I was just going to allude to that, because this is a very, very never-ending kind of a field, a topic, because I think for once the research is quite contemporary, and there is a lot of complicated let's say science and in specific the physics behind it. So
and we still haven't figured out where to place the speakers yet, John. Our home theater is still not designed.
Ron is really
next time.
Sighing, yeah.
Next time, John, you're going to complete the theater.
Next time, yeah, we'll finish it up.
Speak our way.
Okay.
Sorry, John.
Projector.
Sorry, John. Yeah.
Okay.
One of the problems here is you deal with the building blocks of what John is building.
Right.
And if you don't understand the building blocks, it's hard
I
to build a
agree.
building.
Right.
Exactly.
Very,
We're
very,
talking
very well
about
said.
what these things do. And the thing is, when you put them in your room, you have to know what you're doing. You know, that, well,
Yes.
we'll just put this up here and hope for the best. You got to know what they're doing. And
Yeah.
that's the important part. There's no percentage of absorption versus diffraction. There's you got to know what you're trying to do in there, and you know what this thing does and this thing does. So you put it here, and you want this effect, so you do that, and then you know, etc.
Yeah. It's basically a never-ending series of fixes.
I agree.
So
Very
I always like to use this terminology. So acoustics is all about multi-constraint optimization. So each and every case is unique, and so it has to be analyzed. It has to be analyzed in that respect. And I think we got to give respect to that aspect, that each and every case is unique in itself, and what applies to like the famous saying, like what could be poison for someone could be good for someone else.
Yeah.
it's
John
true.
is an expert at small room acoustics. Okay. I don't claim to be an expert at small room acoustics. That's not my field. My field is large room acoustics. Okay. And my field is materials and how they work inside of a space, period. I don't care how big it is or how small it is. It's still the same physical principles.
Exactly.
And so,
Exactly.
so you have to have both sides of this. And that's why this particular format that we're doing right here is actually, to me, is very interesting, because there's a lot of ways of learning here. And but it means, Kartik, that we may be doing a couple more of these along the way on diffusion and other stuff besides.
Absolutely.
And
In fact,
John
we
needs
are
to finish this.
right.
Not even
John-
reached we've not even reached the most important question. How many subwoofers?
Oh, one in each pressure
All you
point.
need is an 8-inch 3,000-watt subwoofer.
Yeah, that's all you need. 50-inch.
I'm teasing because Ron and I were
No,
talking about that.
Okay, you just jumped in something that you
I know,
it's like
I'm
a
just-
quicksand pit. Mars, just so you're aware, I actually participated in a DARPA research project on using sound as a weapon.
Oh yeah.
Ah.
Okay.
Okay, this goes back to the 1950s.
Oh.
Okay, we made a speaker that was around 20 feet in diameter.
Oh.
Hmm.
You're not
Wow.
talking about the LRAD, are you?
Oh yeah, I tested the LRAD. I know all about LRAD, so I can tell you all about it. But let's go to this first one. This one was intended to run at around 2.5 hertz.
Oh.
Wow.
Okay, and it had about 100,000 watts of power pumped into it.
Shit.
And the idea here was that 2.5 hertz, 3 hertz, is a point at which the cell structure walls rub against each other by vibration, and in doing so, they liquefy.
Wow.
So if you
Wow.
take the wall structure of a cell and liquefy it, what happens to the cell?
Wow, finished.
Nice.
My
Yeah,
goodness.
Yeah, it becomes liquefied, right?
It's like Ebola.
Okay,
Mm.
which is going to kill you.
Mhm.
Okay, that was the idea here, was to be able to use this weapon on the battlefield and liquefy the cells of your enemy.
But at 2.5 hertz, won't it be omnidirectional and liquefy your own source of
Wow.
personnel?
This is called military intelligence.
It is highly confidential.
Okay.
Yeah, well, what's interesting here is they built this thing and they put 2 guys out there with a set of earmuffs on
Okay.
to run it. And they turned it on. Well, I'm sorry. Sound doesn't care whether you're the enemy or who you are. It's going to liquefy you. So these 2 guys liquefied on the spot.
Shit. Really?
Oh yeah, they just died. They did like this,
God.
and they couldn't figure out how to turn it off because they had the control of it where these 2 guys were. They couldn't go in because anybody going in would die.
Shit.
Wow.
So they ended up having to figure out how to cut the power to that thing by cutting the main power cables
Yeah.
coming from Boulder Dam. That's where they were originally coming from.
Wow.
And as soon as they got it turned off, somebody went, maybe this is not such a good idea after all, because the earbuds don't protect you from liquefying, basically. So
But-
that was a project. That was a project. That was
I
used.
read, I don't know if you know of Tom Danley. He's also
Oh,
very-
I know Tom very well.
Tom's working on something similar using directed sub energy, using his what's that tapped horn subwoofer technology.
Okay, just for a history lesson. Okay, Tom Danley's tapped horn is based upon the co-entrant horn that was invented by Ralph Hines. Okay, about 10 years before that. Okay, so that was a copycat situation. But again, there's so few speakers sold. If you talk to Ralph about it, he will say, what's the use of going after patents? Because you're not going to get enough out of it to do it. So they let it go. So you're aware, you brought this up, Kartik, that was LRAD. Okay. LRAD was derived from a speaker system that was designed for home stereo, which was a glass panel that was vibrated in such a way that it provided a sound coming from the surface of it based upon various phase functions of the vibration. Okay, so it would give you a very closed in, like a laser thing. So if you walked in front of it, you could hear the sound. If you walked either side of it, it was gone because it was focused right at you. And what it was a carrier of about 60K hertz. That carried the analog on top of it, kind of like an AM radio wave. Okay, that type of thing, or if FM, maybe it was AM, it was AM. So that's what they were designed for, and they produced these things, and they were sold very well at the high fidelity markets. Very nice. They didn't have very good bass response, but they had really nice focus stuff. So from that was derived a company called LRAD that renamed it. And that was used as a communications device between ships on the ocean. So it was a whole bunch of.
I never knew it was used as a communication device. I thought it was used as a suppressor for riots.
No, it was originally designed as communications. It was something you could aim because it had 100 sources lined up by 100 sources.
Oh,
okay.
It's like a line source.
No,
a line source in both directions.
In both directions, yeah. The two-dimensional,
That's right.
It's a hexagonal.
Yeah, and the drivers were 1-inch dome drivers, or actually hard drivers.
So, that is something. So there are many companies right now doing that. So you have a German company which is called what is it called? Marzi Kushru recently allied to that, right?
There's a number of companies doing this, but it was originated by LRAD.
It's called Holoplot. So there's a company in Germany which is doing that Holoplot, which is basically directing the sound towards a focused audience.
Yeah, well, in this situation here, the original unit was about 2 foot by 2 foot.
Right.
Okay, and it was used to create a beam that you could aim at another ship about 5,000 or 6,000 yards away.
Yeah.
Okay, a long way away. And the idea here was that you could focus this thing down so tight that you could focus it using a laser beam on a person.
Right.
So the laser beam would illuminate the person, and that person could hear what was being said, and nobody on either side of them or anywhere on the ship could hear anything else.
Right.
That was the idea.
Very focused aiming.
Right. And you can't intercept it.
Right.
Okay. That means now you have communication between ships that can't be intercepted by radio waves or anything else. So it's very secret. Okay. And that's what it was designed for. So that and they designed it eventually where you could do, as long as you can see the line of sight to the person you're going to, you can communicate up to 10 miles away.
Wow.
Right.
10 miles.
Okay. Right. Yes. And you can talk back and forth as long as you had this thing focused each other. So somebody decided, well, what happens if you, instead of using voice, you put in a two 4K hertz warbling sound.
Mhm.
You go like this, okay?
Mhm.
And you aim it at somebody and you boost it up power-wise to each of these drivers to the point where you got 162 dB.
Holy shit.
Okay. It would become really irritating. In fact, it would burst your eardrums.
Yeah.
And it would make you kind of writhe around on the ground in pain because you'd be bleeding
Right.
from your ears.
Yeah,
Okay.
you'll bleed from your ears.
So these were called non-lethal weapons.
But
Yes.
wouldn't the inverse square law apply to these kind of speakers? So, I mean, once you double distance, you're going to drop 6 dB, won't you?
Well,
That's what
yeah, that's why the line array does things.
exactly.
It's like laser. This is like a laser beam. Does the inverse square law apply to the laser as it does the light? No,
No.
because it is focused.
Right.
Okay, so you don't lose the energy that way either. And so what they did is they created these things to be 8 foot by 8 foot instead of 2 foot by 2 foot. You had longer range, okay, and it would maintain that focus and stuff. So doing that, now you have created a weapon that can be trained on somebody that doesn't kill them but makes them wish they were dead.
Right.
Okay, and they were mounted on board ships for anti-piracy.
Right.
So and that came all out about the Somalia area and stuff like that. So instead of carrying guys on board with guns, they would have these things that were mounted on pivots. And as soon as the pirates would come up, they'd flip them down and turn it on and make that pirate wish he was not there.
Right.
Okay. So that's why you don't hear as much about piracy now as you used to, is because we can basically decommission this person for the period of time he's around in that area and you want to get out of there. So
yeah,
then
kind of like the electronic insect things that keep the insect away.
so they built these to be like 5 foot diameter, round focusing things. They put them on police weapon or police vehicles, and you can aim them at a crowd of rioters, and you can pick out 1 or 2 people who are leading the rioting, and focuses at them and makes them want to go away. Now, the people around them are not affected.
I think Ron, we are touching on sensitive technology. I think it's best left unspoken about.
Actually, it's very well known.
Yeah, it's true, but
the next thing they did is they changed the frequency drivers to RF drivers.
Right.
Okay.
And they produce RF fields that now impinge upon your skin
And cause heat.
and well, they don't heat. What they do is they activate the pain sensors.
Oh.
You don't actually get heated up. You don't get warm, but it makes your skin think that your skin is on fire.
Wow.
Right.
And that's how they do crowd control now, is they aim at people and they go, do you want to feel like you're on fire and laying on the ground? Probably not. You want to get out of there. So they get out, and they can focus on a person at a distance of 300 or 400 yards and make that person want to get out of there. And the rest of the people don't even know what's going on.
Absolutely.
So
Extremely targeted.
Yeah. When we did our measurements, we actually measured how far this thing would go. It would produce a level of 162 dB, 2K, 4K, at a distance of almost 2 miles.
Whoa, seriously? 162 dB at 2 miles. That's amazing.
Oh yeah. It sure pissed off a lot of people, I'll tell you that.
I can imagine.
But yeah, we measured all this stuff at our facility.
Wow.
And I can tell you that the guys who are doing this for years have been doing this. They know what they're doing. I don't usually talk about this a whole lot, but our laboratory does a lot of DARPA work, the defense group. And there's a lot of things out there that people don't know about, that they really don't want to know about. It's the best way I can put it. Cartney, you know what I'm saying?
Yeah, absolutely. I understand what you're saying. There is Keith
has got his hand.
raised his hand for quite some time. So Keith, you want to unmute yourself and ask a question from your side?
Sure. Thanks for having me. I had a question for John, but happy to hear if Ron has anything to say about this as well. A while ago, John and I were talking, and he had mentioned and even showed me imagery of a studio he was designing with a bass trap in the floor under the speaker mixing area to help with some of the speaker boundary issues. I was just curious if John is still doing that in his practice or not.
I have designs for that. I'm waiting for somebody who can afford to do it. It's I use a steel grating on the floor, and under that are anechoic wedges that refuse to allow any reflections out. So what it does, you get speaker bounce no matter where you're at. Even if you have flush mounted speakers, it's going to hit the floor, it's going to bounce up. If your desk is there and blocking it, that helps. However, you're still getting that elsewhere. That's why I invented the diffraction desk, the Borg mixing desk system for in the box working. But the floor bounce is a concern to some, and that's a solution. We'll see. I know Tom Hidley
use the home theater solution. Put a carpet on the floor.
No. That'll cut the reflection at about 2K. 2 kilohertz, but the lower frequencies then affect it.
Yeah, it's like you need a carpet 10 feet thick.
Yeah.
In fact, if you look at the picture of my arc, you'll see the wedges on the floor around the arc. They're 5-foot wedges.
Holy whoa! Okay.
Okay. And they cover all the area for all measuring, so that way the floor doesn't give you a reflection when you're measuring. But I had to have 5 foot tall wedges to do that, and it covers an area of about 10 degrees on either side.
So John, if you're doing that in the studio, you mean the studio floor is raised up by 5 feet?
No, it's not raised.
Oh, it's dug down.
Oh, yeah, we dig a hole.
Okay.
dig a hole.
Oh my
Put it in the hole. Yeah, and we put a grating over the top of it, so you just walk across it. It's not a big deal. But under there are the wedges. That's
Or I can imagine right now, if I was talking to John, I would say, John, just make a 2-story studio and put the bottom, just leave a hole in the floor to the bottom floor room, and then put the wedges down there.
Wedges.
Yeah. And now we've got another problem. We got a windowing happening. So we got a reverberant room downstairs, and we got this grid thing coming up. So it's windowing everything back up into our mixing room, and we're screwed again.
Yeah, this is what happens when you have way too much time to imagine things.
That's absolutely.
John, do you have any of those pictures that the guy from Egypt put together for the recording studio in Saudi Arabia? Okay, why don't you bring up one of those, the performance room and the recording room with the glass front?
Okay, just a second. I gotta get over there. Oh, let's see.
So while you were looking, we were talking about the measurements we did with those spline walls, with the curved walls and stuff. You're going to see how they were used in this situation. And in this situation, we have a recording studio where the entire front wall is solid glass, and the speakers are mounted in the glass wall.
Oh wow!
Flush. I hear somebody laughing.
Yeah. These are the renders. Okay, I don't have photos yet, but these are the renders. This is the control room. This is looking from the tracking room into the control room.
Oh, that's amazing.
I have a glass front wall, speakers hung in the wall. This is from the other side, looking at the tracking area. This is that wall right here. That's spline. This is what I call an optimized spline. It's based on a prime or primitive root sequence.
Is it only in one dimension, or is it splined in the second dimension also, as in the horizontal? Like, so does it from ceiling to floor? Is it also having different?
No.
Okay.
No, it's let's see, where am I? Oh, this and this. Oh, here it is. Okay. So no, it goes in and out. It's just spline, it going in and out. It's like a snake on the wall.
Right.
Yeah. The idea here was to try to unite the performing space and the recording space in such a way that you felt like you were in the room with them.
It definitely does that. It's amazing.
Yeah, and if you look at the wall of the glass wall, it's a 2-layer wall. One is flat on the side of the performance, and the other side is curved.
Oh, it's curved. I thought it'd be
Yes.
Yeah, this side, you can barely see the edge here, right here on the floor.
Oh,
Now,
yeah,
this is a render, mind you. This goes here, and it's got a seam right about here. I think you can see a little bit something here. Same way over here, there's a seam here. And these are angled from the plane, from the flat plane in front of you. They're angled in 25 degrees.
Right.
Okay.
So there's three different plates of glass.
Yeah, there's 3 different plates of glass here. On this side, this side,
It's flat.
there's one piece, and it creates the.
You can see this on the floor. You can see the angles, the splays.
Yes. Yeah,
Right.
there
you go.
Yeah, and the whole point here is in order to make it soundproof, you had to have a lot of space in between. Okay, so the actual wall thickness at the center is around 30 inches.
Oh, 30 inches. Wow.
Yes, yeah. This is a very, very thick, and the glass itself is 1-inch laminated glass.
Yes.
Each layer of it. So there's multiple layers of this stuff. So it's a very, very expensive proposition to do this, especially when you cut holes in the glass to mount these speakers, and they're mounted on resilient type channels and stuff, so they don't vibrate, and they're resiliently mounted in the glass, so they don't vibrate the glass and all kinds of stuff.
Did they actually build this? Did they build it?
Yes.
According to the guys I talked to, they actually built it, and they are extremely happy with it.
Okay.
Oh, that's great. And that's really
But
exciting.
they also had a budget of around $1 million to do this.
And
This is Saudi Arabia, a place called Jeddah.
Jeddah.
Yeah. So that's where this is at, and it's a college where they teach people how to run sound and stuff.
Yeah.
But yeah,
Pretty
John
cool.
and I worked together on this project, and so this is a situation where I had some ideas, he had some ideas, and the 2 of us together came up with this thing, and it's one of the more, what do you call it, more forward-looking studios that we've ever designed, or I've ever designed. And so we tried a lot of different things, and it took us about 6 months to design this thing.
To get it done, about 6 months. Yeah. Take some time, because we went through the soundproofing. We these special studs by Safeco. Scafco. Yeah. And
special materials, all kinds of stuff. I mean, every trick that we know in the book that's available to us, we use in this room.
Wow. That's what you do every time. When I design a place, I pull up the most current stuff that I know, and what works and what we need. What do we need? We'll put it here.
Was this project funded by
evolving.
Was this project funded by the government of Saudi Arabia?
Yes.
Or was it?
Yes.
Okay.
Yeah. And there's actually this room, and there was a performance hall as well. And I don't know, John
did this performance hall. Did they finish that? Did he say?
No, they didn't. They're still working on that. But this is the place I was telling you about, where we took the ceiling and we used a lot of partial sphere sections and put them on the ceiling. Yeah. So that's how we covered that, along with the walls. We did on the walls as well.
We call partial sphere sections in India, we call them gamelas. We use them to carry sand and cement.
Oh yeah.
Yeah. There you go. Inverted, right? There you go.
Right.
Yeah. So I mean, the idea here is we're trying to share with everybody here what works. It means you have to change a lot of times what you think works versus what really does work. Right. And that's one reason why this particular thing you're doing, Kartik, is so important, because I've talked to other guys that have been here before and participated in number one. They want to know if you're going to post this on YouTube, and I said, as far as I was aware, you were. And the next question was, when are we having the next one?
Exactly.
So,
Yeah.
we can keep you busy for a number of months doing this, and I don't think we'll ever cover the same things over and over because there's so many things, especially in the area of absorption and diffusion that can be covered in here. And we can have a 2-hour session or 3-hour session on just certain types of diffusers.
Right.
I think that would be a great next session if you're up to it. Different diffusion. That would be fantastic.
Well, that's what John and I have talked about along the way, and the more we do
Ron,
these things,
what I would appreciate is if we could come up with a little bit more scientific, like share some formulas and papers and talk about how you got around to it that way.
I will tell you this: I was going to do 2 papers, one in Torino and one in Tokyo, on this absorption thing, and I had to cancel it because I can't afford to do those trips; they're too expensive. Going from here to Torino was roughly around $4,000 for the airline fares. Going to Tokyo was around $4,000, and this entire place is supported on my Social Security and whatever I make testing, which is never enough to cover all the costs. So I had to cancel both those. I'm still planning on coming to Sydney, Australia in December for ASA. To present a paper on this, and I'll be presenting that. But to be honest with you, I have all these formulas and I can pull them up. I don't have them right here in front of me right now, but I can pull them up and we can have them for the next meeting. And Kartik, you were asking about the integrals. This includes all these formulas.
Right.
For doing absorption.
Awesome.
Okay. And diffusion, I'm not sure what you can do in this situation other than show the actual GLLs now.
Right.
Yeah, that'd be great. That'd be great. That gives an idea of what's actually happening.
So in that case, John, probably the best thing to do is we can schedule something where we can take your 604s and your 511s and stuff, and we can put them on to Speaker Lab, and I can show them and go through the process like I did with you.
Yeah. Yes. That would be good. You know what? I could load up one of those diffusers you sent me a long time ago that you tested there, and we can show during the conversation. I can put it on my screen and you say, okay, now do this and show this.
Okay, do that.
We could just do that.
Guys, do we have a few more minutes?
Sure.
Okay,
Maybe
we're gonna. John, to be honest with you, why don't you show the 604-1?
604-1.
The one I just sent you.
Yeah. 604. Okay. Oh, now, yeah, 604 is great. All right. So here it is.
604-1, not 604.
Oh, you didn't send me the -1.
Yes, I sure did.
This was the 511 you called.
That's the third one I sent you, but that would be fine too.
But I missed it. Oh, this is that I'm thinking was for the other one. But here, this is
that's the 511.
That's the 511 -1, or yeah, the 511. Okay.
Yeah. So either case, so this is what comes up from Speaker Lab. You show a picture of it, and you can now see that from the front it's variable depths and stuff, etc. Okay. Now, John, go up to where it shows calculation. And do calculate balloon. Okay, and now set that for 5 degrees. Okay, set it for 4 meters. Just type in 4 meters.
Okay.
Okay, go down and take the check mark out of the air absorption.
Okay.
And put the control up there at AES broadband.
All right. Okay.
Okay, and hit OK.
Oh,
nice.
Fantastic.
Okay. So now you can see what it's going to do. Let's see if John, you're going to have to
1,000 hertz.
Yeah, this is 1,000 hertz. Now go up to the
let
top.
me go to third octave. Let me go to
third octave. Okay, so there's third octave. Now set it up for do an alternate Y.
Alternate
on your keyboard. No, Alt Y.
Oh, okay, yeah. Alt Y. Okay.
Okay. So now you're looking right down the gut of this thing. And what you can see is the sound is coming in from the center, and it's coming back out of the center, which means this is basically a spectral reflection coming back right back at you. So this level that you're seeing here, the white is no attenuation of any kind. The red is anywhere from 3 to 6 dB attenuation, and as you go down on the thing on the side, you can see the delays along the way. So, John, you're going to have to become the presenter again in order to come up, because it's coming up right now.
Oh, okay. I'm here. Can you see this?
Yes.
Everybody see this.
So now what you can do is go up here to the top where it has frequency.
To the top, yeah.
Click that and then re-click it. And now use your arrow down or up keys to go upward.
Okay, we're going up to 1.25K, 1.6K, 2 kilohertz, 2.5, 3, 4.
Yep.
Now we're starting to get something at 4, 5.
Yeah. See it starting to spread horizontally. There you are. This is where maximum effectiveness is.
See, at 6.3, bam.
So leave it there at 6.3.
Okay.
Now hit Alt Z.
Alt C.
This is along the Z
Now
axis.
now we're looking. The Z axis looking down on it.
Mhm.
So now you can see the coverage in a horizontal plane.
Right.
Okay.
The plan view.
That's right.
Yes.
Now you can see that it covers almost 150 degrees wide.
Pretty good.
And if you notice the colors, it's barely down. It's only down 3 to 4 dB, 5 dB down from the original sound.
Okay.
It's a reflector.
Yeah. So now if you look at the green, that is down 20 dB. You're not even worried about what's in there. Okay. So now take it to a X view. So do Alt X. So now we're looking at it from the side. So you can see
there's hardly any vertical diffraction at all.
Right. So strictly horizontal.
Yeah, and that's what it's designed for.
So now do an Alt 3 now. Now take the slider bars on the bottom and slide the bar around. And we can look at it. And if you want to take the slider bar on the side, the right side, it changes it in the vertical view.
You tilt it, tilt it up and down.
So the way you've got this is you've actually measured this and then exported it to. Oh, okay.
Yes, this is an actual measurement.
Okay.
It's the data from an actual measurement.
Now,
whoops! What happened? Where did it go? Wait, where did it go? It died.
It died.
Ron,
Did you close?
it died. It died. No, I didn't.
Oh, there it is, right there.
It just
right
died. I know.
Okay.
I have to reset. Everything.
Yeah, if you try to move it too fast, it won't redraw fast enough, and it'll crash. So set it for 4 meters again, and then get rid of the air absorption, and calculate it again. Now, what I want to do is I want to go to the graphs now.
Resolution, 5. Okay, we're going to go there. We're going to go to.
So go back to 6 point. Yeah, go back to 6.3. It doesn't matter. You go to 6.3. So go up to the top up here where it says graphs.
Okay. 1 second.
It won't matter. It won't matter.
Oh, okay. Graphs.
Go up to graphs. Okay. And go down to the horizontal map. 2 down or so.
Why can't I see it? Oh, there it is. Okay. Horizontal map.
Now do Alt Z, Alt Z, Alt Z. Okay. Now you're gonna have to bring us back up. So if you look at this, this is the coverage of the entire balloon laid out in a flat map. So if you look at it from the left side, it's low frequency at around 25 hertz. And if you go to the right side, it goes out to 20K. And what you're looking at horizontally or vertically is the coverage. John, I have to bring you back up again.
Yeah, so right here. Okay, sorry. Thank you.
So what's happening here is you can see here at about 125 hertz or so, it covers all the way across, which is basically 200 or 180 degrees. you look over in the side here, you can see the coverage on the side. Okay, so as you change in frequency, as you go towards the right, you can see the coverage patterns change over on the right hand side. So this is a view of the horizontal coverage of this thing laid out at all frequencies at the same time. Now do the vertical map.
No.
John, go.
Yes, vertical map. Sorry.
Yeah, just hit vertical map.
Vertical. Sorry. Okay. So this is the vertical map.
Okay, except that you got to do Alt Z again. There you go. So now you can see vertically, it doesn't do very much, except at low frequency. And as you get higher up, it narrows down to just maybe 5-10 degrees vertical.
Yeah, not a lot.
Okay. So that's a way of displaying that balloon in a flat map.
See.
Okay. So now let's go up to that that graph again, and go down to what is it? The beam width.
Beam width. Here we go.
Go horizontal.
Horizontal. Okay.
Okay. So what you're looking at here is the area that is blue doesn't count in this unit.
Mm-hmm.
And here's why. It's a 2 foot by 2 foot unit. Do you honestly think you're going to see it at 125 hertz?
Mm-hmm.
Not really.
Yeah. So what you're looking at in the Johnny, you're back. You've got off to here.
Okay, I'm here. Yeah, it doesn't.
So that's why we blocked it out. You're not using this area. Okay. What's usable here is from about 3K or 2K, whatever it is here. I can't read the numbers. Up to around
John, can you just maximize your screen, John? Maybe share your screen again, John.
I am sharing it. I am sharing it here.
Now it's better. Now it's
okay. You want to pin my screen right now, Kartik?
Yeah, just 1 moment. I'll do that.
Yeah. If you just pin it, then I won't.
I've done that.
Okay.
Okay. So you can see that we're doing coverage here of about, and I can't see your numbers, John, because they're so blurry.
5K right here.
It's 5K.
Right.
To 16K here.
You're still not pinned.
Really?
It is pinned as far as I'm concerned. I have pinned John's. I have pinned John's screen.
Yeah, I see your face.
Okay, you see my face now?
Yeah.
No, I see your face now.
What about this? What about this? Do you see this?
I see it now. Yes.
Okay.
So now, if you look from here, which is around 20 degrees or so, I think it is 20 degrees over here on the right side. If it goes up, it goes up to around 120 or 130 degrees at the peak at around 4K there.
Yeah.
Look off to your left. You can see the.
Oh, here.
No, the left, all the way to the scale. Scale all the way to the left.
Okay, all the way to scale.
That'll tell you how many degrees of coverage it has. So if you go to this peak over here and go back here, you can see it's around 90 or 100 degrees or so at 4K. And at 8K or 12K, it's a little bit higher than that. So this gives you at least an idea horizontally what kind of coverage you have over what frequency range.
Right.
Okay. Now go the graph and do the beam width vertical.
Beam width vertical. There we go. So vertically, we have little to nothing.
Hardly anything. That's exactly it.
Yeah.
Okay. So now you can also compare this. Go to your graphs again, and go to the polars. And pull up the polars and set the polar frequency at 4K.
A quick question here, Ron. What would be the angle of incidence of the sound on
all these have an angle of incidence of around 3 degrees.
Oh, 3 degrees. So if and that's why we are not getting much vertical dispersion. But if we had an angle of incidence of say 30 degrees, then would that raise the vertical dispersion?
Well, you'll see the dispersion go up, but the level will be 20 dB down.
Oh, okay.
So this is why I say we've done experiments where we've done the angle of incidence going from 0 to 90 degrees. And we found that really the only usable data came out of between 0 and 15 degrees.
All right.
And the difference in there was so minimal that you really just could pick out an angle that was like 3 or 4 or 5 degrees. So you got some horizontal movement.
But that's great because then you're not firing any energy either into the floor or into the ceiling.
That's exactly it.
Right.
Okay. So So this took us about a year of experiments to figure out where was the ideal incident angle to get the maximum information that we could use. And we found that between 0 and 5 degrees.
So this has to be placed on the wall at a certain height from the tweeter of the speaker.
No, not necessarily.
Not
You know,
necessarily.
sound coming in will go through here at an incident, and if it comes in as any kind of incident between 0 and 15 degrees, it's going to give you about the same results. Anything beyond that, you're not going to have enough energy to worry about measuring.
Okay.
Okay, so back to our picture there. If you'll notice at 4K or whatever it is.
This is 4K.
Right.
Right
So now
here.
you can see the vertical and horizontal overlaid. So you can see the difference.
Which is horizontal? Blue is?
Yeah, blue is vertical and red is horizontal.
Red is horizontal. Okay.
So these are standard polars.
We
Very
go up to where
understandable.
it really starts working is 6.3K. You see how it
There you go.
balloons
See?
out right there. See?
Go up to 12K.
And then 8, and then it drops back down. Then 12K, it pops up again. See?
Yep. Okay. So this is a way of displaying this stuff that people who use speakers can understand quite nicely, because this is how you describe a speaker polar. Okay. So that's why I say we can use this just like we do a speaker, and we can put this on the wall, and it will act like this with the sound coming off the wall. So there's all these capabilities here. Frequency wise, John, go up to the graphs again.
Graphs. Okay.
And go down to, I think it's the you have to go above, go up. I can't read the thing. Keep going. One more. There you go. No, one more.
No, transfer function.
Yeah, transfer function.
Okay.
Okay. There is the frequency response on axis.
Phase overlaps.
Yeah, there's phase and magnitude both. So the red is the frequency response and magnitude, and now the blue is the phase response. Now, if you'll look, we had a 360-degree shift at flip at that point, and then it continued on down. Yeah. So if you continue, John, again, I don't see your graph here. It flipped again.
Sorry. Yeah.
Okay.
Well, here,
so it goes all the way down until you hit around 2K. Keeps on decreasing. Now look at all the flips that occur between 2K and over here to 4K.
It's constantly flipping.
Yeah.
Yeah. Every time the phase flips, this means you're going to hear more of that openness.
That air.
That's right. So that's why if you look at this, you can almost look at this thing and say, where is it going to work best? It's going to work best between 2K and 4K, and another time period between 8K and about 14K. Okay. So this is what this particular software allows us to do.
Phase flip in the low frequency? What is that? Oh, we're not looking at it, is it?
That's the size of the unit. Okay. This is based on those 2 foot by 2 foot. That's what that does. It's just a specular reflection off of that whole piece.
That's exactly it. So yeah, so you figure this 500 hertz is the size of the sample. That's the point. And what you're doing, you're seeing a reflection of the plane wave coming off the flat surface, and you're seeing it flip. So that's why it's no use to you, because it is a specular reflection. Okay. So this is the kind of data that we're trying to produce now. Nobody's ever had this for diffusers previous to this, ever. Even if you look at the scattering coefficient, what does that tell you? It tells you there's a certain amount of energy that, quote, is scattered. It doesn't tell you anything about its characteristics or anything. It's just scattered energy.
But isn't this graph of the phase showing us that there's a huge delay between what's this? I don't know. I can't read that. It's 63 hertz and 2K. I mean,
yeah. Well, that's because it's a 2 by 2 sample.
Okay.
So if you have a 2 by 2 sample, it doesn't matter what the detail is on the front surface. It's still a 2 by 2 flat plane.
No, I'm talking about the delay. There's a delay. It's lagging, right?
Well, there's a phase shift, yes, and that has to do with the fact that you are converting a curved source front.
Okay, planar from a spherical to
plane.
planar. you said.
That's right, and that's what you're seeing is that phase shift in order to change, convert it to a planar type thing.
And then in this section, these are all the planar
Reflections.
Reflections.
Yeah. It's it has a lot of data in here. John, last one, go up to graph, to graph, and go to phase balloon.
Phase balloon. All right.
Oh my lord!
There it is. See, we're at 12.5 kilohertz.
Right. So
And
now go back
spiky.
to 125 hertz.
125. 125. Okay.
Yep.
Point.
Now rotate that three. Just do an alt 3.
All three.
30 degrees. Okay.
It's just an alt. It's just 3D view. So
Yeah.
what you have is all these points where they form like a pedal all the way around. You notice they all stop at the same point. Okay, those are all phase functions
Coherent.
that are
right?
coherent. That's exactly it. So the more it looks like a flower petal, the more coherent the information is.
Mhm.
So John, bring that back up and go up in frequency to say 1K.
Now it's
See,
getting a bit
We
jaggy.
got
starting to break up, but it's still a lot of
It's very
coherent.
coherent.
coherency
That's
here.
right.
Still a lot of coherency.
Yeah. So take
Mhm.
it up to 6K now.
All right. There we go.
Wow.
That's
Now
three. That's three.
So it's starting
that's
to look
4,
more and more like a
5,
sea.
6Ks, the porcupine.
Right. It looks like a sea urchin.
Sea urchin.
Sea
yeah,
urchin.
sea urchin.
Okay. And the more spikes you have, the more this thing is going to sound like a source of space.
Mhm.
Okay. So now go up to 12K or 14K.
There's 12.5.
Yeah. So you can see it virtually has a phase change every time you move any angle.
So
You
this
rotate that around if you want to. You can rotate it around.
Yeah.
I mean, it's just like, it's
Fantastic.
Yeah.
and that's where we can tell whether it's going to give you a diffusive sound or not.
This is diffuse, right? This is no
Yes.
Well,
This is
yes.
diffuse.
Totally diffuse.
Mhm.
Totally.
This is diffusion. This is diffusion in phase,
Phase change.
not in magnitude, in phase.
Mhm.
And this
Correct.
is what your ear responds to. It doesn't respond as well to magnitude as it does phase. And the reason is you have
20
two ears.
kilohertz.
Well, it's not only that. You have in magnitude, your eardrum is a pressure sensitive microphone.
Mhm.
It only responds to magnitude in one ear. Okay. But if you have two pressure microphones spaced in space, then the arrival of phase arrives at different phases at the pressure point, and therefore your brain interprets that as a time delay, a difference, and that interprets into space. So this is anybody familiar with a microphone company called Microflone? Guys?
Sorry.
I'm not.
There's
I
a
don't-
company out of Germany. It's called Microflone, FLOWN.
No, I don't know.
They have a microphone. It's called a kinetic microphone. It's used for measuring velocity, not pressure.
Mhm.
And what it is, it's two different pressure microphones spaced in space, face to face. And there's a space between. So
Alright.
there's a different time arrival. And there's a software package that takes that time arrival and converts that to a velocity. So you can tell how a velocity microphone is what it is. That's what you're measuring here is the velocity differential.
Could we see the magnitude balloon if there is one? I mean,
Well, you're seeing that all the time.
The
Go
frequency
back
balloon.
let's go back up. John, go back to the graph.
Uh-huh.
And
Yeah.
go to the second one down. Second one.
Horizontal map.
Nope. No,
Horizontal
the one
map.
right above that. The one right above that.
Continuation balloon. All
There
right,
you go. That is a magnitude balloon.
Mhm.
This is here.
If you look over in your right hand side, you'll see how many dB down it is.
No, I got it. This is what we saw earlier.
Yeah, those are the magnitude balloons. So you can see now the magnitude balloon looks very different than the phase balloon does.
Totally.
And you have to keep both of them into account for your ears. because your one ear by itself hears the magnitude balloon. The two ears together hear the phase balloon.
Yep.
And your brain conflates those two together into space.
If you look at the 12.5 magnitude balloon and the 12.5K phase balloon, is the dispersion different? Because do you have like a dispersion angle in the phase domain?
Well, you only know that it's only 180 degrees. That's the maximum it can be. But there is nothing out there that we have a graph of that describes the dispersion balloon of phase. It doesn't exist yet.
No, so like if you look at this balloon right now, we see if you rotate it on we're facing it, you'll see that it is going all the way 180 degrees, right? Right.
So now, John, go to the graph of the phase balloon and hit Alt Z.
Yeah, I just did. Yeah, got it.
Okay, so look down on it. That is the dispersion angle of all the phases.
Correct. So, but in the frequency domain, the magnitude domain, we don't get that much dispersion.
That's, well, we get 180 degrees in the magnitude. Yeah, go back to the magnitude balloon. Get John the second one down. See, wherever the red is.
It's only 150, right?
150 or so. So yeah, there's more dispersion of the phase than there is of the magnitude.
Mm-hmm.
But if you look at the magnitude, wherever you see red, that's all within 3 dB.
Okay.
Okay. So as your ear is concerned, you're not going to hear the difference. It's going to sound equally loud at on either side, 90 degrees on either side, than it is the center. Okay. Yeah, that's the hard part about realizing here is you're looking at attenuation here, and your ears cannot really discern anything less than a 3D difference for most people. But look over the phase now. Phase is all over the place.
Yeah.
Now I can tell you right now that the reason you don't have these other graphs is because they don't really have any application in speakers, phase and stuff.
Mm-hmm.
But in our area, they do. So what we've been told by the people who do the software is as soon as there is a standard in place that describes all this stuff, like ASTM or ISO or whatever, they will then come up with some graphs that do the same thing, like polars for phase, and give you like the beam width of the phase response. And then we can say that the higher that differential goes, the more dispersion there is, type thing, more stuff. And we can describe all these things. We've already done that. We've done this by hand. We calculated where every single point was by hand on an Excel spreadsheet and created graphs and stuff like that.
Yeah.
But they're not going to go through this process of changing their software until there's a market for it. And that's what we're creating as we measure things. The more and more units we have measured that are inside this GLL function, the more of a market there is. And all of a sudden they're looking at this going, well, geez, if 99% of the people out there are looking at diffusers this way, then maybe we need to create the software to allow them to look at this stuff.
Oh yeah. Oh yeah.
So it's kind of like what comes first, the chicken or the egg? Well, sometimes it's the egg, sometimes the chicken. And as other people would say, sometimes the female chicken has to come first.
Yes.
So I think the whole point here is that we're in an evolving area of simulation. And how can we best describe things simulated wise? There's a gentleman out there, and I will name his name, Christian Carvin, who is a great believer in simulations. And I agree, simulations are great. The problem is all simulations derive from data first. And he's kind of going from the other direction. It's like, well, we'll create the data from the simulation. I'm kind of going, doesn't work that way. Okay. But so we're trying to convince him that let's get the data first, then we can create the simulations. And he's kind of going, well, let's create simulations because then we can predict the data. No, you can't predict the data. So yeah, so it's a matter.
That single statement has rendered all theoretical physicists obsolete.
Well, I don't think
really,
I don't think we've related all of them obsolete, but we've sure changed the crap out of them. basically everything we've learned for the last 80 years is suspect.
It has to, and it remains so. As
Yeah.
long as it remains so, we search and we look, and that's what we need to do. And we need to keep looking. We need to keep testing and keep looking. As soon as someone stands up with, I have the whole truth, and it's everything, and that's it. There's no questioning it. Well, we're in big trouble. So,
Yeah.
yeah.
I think the key here is all the stuff we're researching right now is stuff that is what's called standard generic stuff.
Yeah.
Nobody in the industry has ever wanted to pay for that research because it doesn't give them an advantage in sales. Okay, companies are very profit oriented. It's like, if it doesn't help me increase my profit, we aren't going to do it. So you have to give it to people like John, and I will give John all the credit in the world. Okay, John, I'm going to tell some people something, and you may not. I hope I have. You're not going to kill me for this. Okay.
No, it's fine. It's okay.
John has invested well over $26,000 in the last 2 weeks or 3 weeks in testing. Okay, out of his own personal money, so that we have this data like the 706 and these GLLs you have here. So you got to give John a lot of credit for putting his money where his mouth is. Okay, and he's already partially committed to increasing that level as well. Although I don't know at what level he's going to stop, because it's going to be okay. This is going to bankrupt me at some point. Okay,
well, it's not. I'm going to make it. We're going to make it work. We're probably going to do that much again. I'm serious.
Yeah, and so this is all eventually going to go into one of his books on materials. And there may end up being a book on absorptive materials, and there may be a book on diffusive materials. And we can create cut sheets for all these diffusers by just having all these little graphs and stuff and putting them on a cut sheet, and you can actually see what a diffuser does, and then you can pick your diffuser based upon the performance.
Correct.
Yeah, what you want it to do.
That's the way it should be, right?
Yeah, and one of the things that happens is right now we pick our absorbers based upon their name. Okay, I'm sorry.
Or the NRC value, which is
or the NRC value. And ever since I've been doing modeling with ease, I look at the database and I go, what do I need an absorber to do? And then I'll go look at the curves and see if I can find a curve that is the opposite of what I want. And I'll pick that absorber. I don't care what it is. It could be called Timbuktu. Okay, it's going to go in there because that's the material I need. And that's how I've done my design work is based upon what I need it to do rather than what the name of it is. In other words, you can have Armstrong Ultima. Okay, great. I don't care about Armstrong Ultima. Now, if it has a nice curve, it does this at the frequency I want, then I will put Armstrong Ultima in that job. Okay, because that's what it's there to do.
But Ron, that's exactly what you're trying to do is what the speaker companies have done, right? I mean, many people buy speakers just by brand name. Nobody actually looks at curves and stuff and says, oh, this one's maximally flat and this phase response is this way and the frequency response of the speaker is this way. No, it's a B&W, it's a Nautilus. I want it,
Yeah, I know. And that's why we measure. And sometimes when we measure, people are not happy.
Yeah.
Okay.
We got stories about that.
Yeah, you have a whole bunch of people that are unhappy about that. The reason you see a lot of this data today is because of something that happened about 25 years ago, and I was part of that. Okay, there was a convention center in Boston that was put together, and they had all these speakers up in the lid, and they aimed down and they said, "Oh, it'll cover this. It'll give you intelligibility like this. It'll do this. It'll do that. Do that." And they built the place based upon that design. And when they opened it up, they found out that the performance of the speaker system in the room was nowhere close to what they said it was going to be. So there was, typical US, lawyers got involved. Okay.
Oh, wow.
The city of Boston sued the contractor, who then sued the consultant, who then sued the manufacturer of the speaker.
Wow.
So now you've got to figure out who has the deepest pockets. Okay, and you keep on suing, you keep on suing. So I ended up in court finally having to testify. And what it was I had measured the speaker, and I had sent the speaker measurement to the manufacturer, who then had it looked at by their marketing people. Now, the speaker itself was marketed as a 60 by 40. When we measured it, it was more like 90 by 70.
Oh, okay.
Okay. But marketing didn't like that. So they forced the people who had the data to change the data so it looked like a 60 by 40. Okay. So when it was put into the program, it acted like a 60 by 40, which the real speaker didn't do. Okay. So the performance was predicted wrong to begin with because the data was affected by the manufacturer's marketing department.
Fudging.
Yes, a lot of fudging. So what happened was when I showed the original data, I showed them that it was not 60 by 40, it was 90 by 70. And the court went, well, why has it changed? Well, then all of a sudden, the company that made this particular speaker, which by the way doesn't exist anymore, the company went out of business. They said, well, our marketing said that this is what it's supposed to be. Well, and the judge said, well, I know what it's supposed to be, but it's not. So why didn't you create a speaker that did what it was supposed to do? And the engineers didn't have any answer for that. So eventually what happened was the speaker company was found to be liable for this. And the award was like $5 or $10 million. And that bankrupted the company. And they went out of business.
Community sound.
No, Community still exists.
No,
but
Community was bought over by Biamp.
Oh, it was by it, yeah, but it still exists. They actually sell Community speakers yet. Okay, but no, this was before all the buyouts were going on. Let's put it this way: the first letters of the company are AL.
Oh, Altec Lansing.
Yes. You notice there are no more Altec Lansing speakers. Okay, they were one of the old companies that went back to the 1930s.
Yes.
Okay?
That's bad management right there. That's what happens when you have an old company, got new management, and they make dishonest decisions like that.
Well, what happens is this is when you allow marketing to control engineering.
Yeah.
Yep.
Okay.
Yep.
So what happened was the word got around in the industry that Altec went under because of this court case, and they all came back to me and said, "Well, why did you testify in this way?" I said, "Because it was the truth." And their comment was, "Well, what do we have to do to prevent this from happening again?" I said, "Well, my suggestion is you get your speakers measured."
Yeah. Oh yeah.
And they said, "Who's going to do that?" I said, "Well, there's me, and there's Pat, and a couple other guys that can do it, but there's only about 3 of us in the whole world."
Pat from Synodcom.
Yes, he started the whole process of doing that. But the problem was he didn't have a way of measuring it, and then there was nobody else that did. So he produced a way. But I find our measurement systems are better because we do it simultaneously rather than one at a time. So he has to have a microphone moved to all these 3,000 positions, and it takes 6 hours to measure a speaker, which means it'll change air and stuff like that. We can measure the whole thing in less than 3 minutes.
Okay.
Because we do 19 simultaneous measurements at the same time as we rotate, and we do a set of measurements every 3 seconds. So it's like, yeah, you can do that very quickly. But the point is that it forced the other companies to start to be honest about things. And my first company that came to us was a company that still exists. They were bought out by, I'm trying to remember who in the hell they were bought out. Maybe MSC, maybe, or something like that. A company called SoundSphere.
Oh, okay.
Uh-huh.
And you remember those?
Yeah.
Yeah.
They were kind of a joke in our industry because it was like they didn't actually do what they're supposed to do. Well, we got a chance to measure them, and we actually showed what they actually do. And they were ugly as anything. They had to be the ugliest things I've ever seen in my life. And I sent the data back to the guys at SoundSphere. And I said, "You going to post this?" He says, "Yeah." I says, "It's not exactly what you think it does." He said, "It doesn't matter." He said, "If we post these, people are going to know that they're real because they're ugly." and lo and behold, they posted these things, and they got all kinds of good comments from the consultants saying, "Yeah, we know it's ugly, but we know it's real too." And so they got all kinds of good stuff about that. And people bought a lot of these things because they said, yeah, it doesn't do exactly what you said, but it does certain things that are useful for us. And we can use them in certain areas that we can't use in other areas. And therefore, they started selling more of their sound spheres than they used to. Because before it was unknown how bad they were, that we just knew they were bad. We just didn't know how bad they were. But as soon as you know what the how bad it is, now you can make the how bad good by using them certain ways. And so all of a sudden, other companies started, hey, that didn't work out like we thought it was. So all of a sudden, we got buried in measuring speakers for like 3 years. And we were measuring speakers upon speakers upon speakers upon speakers. We measured over 600 speakers inside that 3-year period. Wow. And most of them were not very good. But what was interesting is the results we got from the consultants. The consultants said, we don't care whether they're bad or good. We can deal with bad and good. We can't deal with the unknown. And so all of a sudden, we got all these companies coming to us and say, okay, we're not going to bother these things ever again. Whatever the data is, whatever it is, as ugly as it is, it's ugly. Okay. Now we put it out there, and all of a sudden the consultants came back and said, hey, it ain't a problem with being ugly. It's a problem with being unknown. Right. And so that's why you see so many databases for ease of manufactured speakers, because they've all learned that consultants will not specify your speaker anymore without ease data or balloon data. And you can have CLF as well. And
you need to tell that to the Chinese, though.
Yes, we know. We're quite aware of it. It took us 10 years to get all the U.S. and European speaker companies to realize this. The Chinese have not figured this out yet. But as consultants, when I was a consultant, and that's all I ever did, I'm sorry, you don't give me data, I will not specify your speaker on a project, period. Don't even call me. Not even worth the effort.
Right.
And the more and more consultants that do that, the more people always thought consultants don't have any power because the manufacturers have the power. Consultants are users. They don't have any power at all. And I told them, I said, look, if you don't specify their equipment, they don't sell anything. If they don't sell anything, they go out of business. So guess what? You have the ability to say, you don't give me the data I want, you don't get specified. All of a sudden, now there's a monetary reason for measuring. And when you look at the sales loss, say 1,000 speakers lost at $1,000 a piece. The cost of measuring in $1,500 is nominal. And that's when they all started doing this and going, oh, well, yeah, okay, that's actually not a very bad cost effect ratio compared to sales. So, you just got to hit the manufacturers where they live, and that's called the dollar or the money, whatever it is. And if they see that they're going to lose money, kind of like what's going on with Anheuser-Busch light beer. It was like, ooh, okay, we're not going to sell your beer anymore because you did this with this. It's like, whatever the reason is, the point is the people out there do have the ability to make a business really hurt. If you piss off the general public, they will piss on you. And people don't realize that until they get hit. And it's like,
well, there's enough competition in the market that you got to be smart. You got to do what's right.
Yeah. Well, the people who did this Bud Light thing, I don't know if you followed it or not, but they got put on permanent leave.
Yeah. Well, they went woke and they went broke.
Yeah. So now they're still trying to recover, and now I guess it's affecting other brands of theirs as well, like the bats and stuff like that. So it's like all of a sudden they're going, okay, this was not a good thing for us to do. Okay. And it's one of these things where, does free speech exist? Yes, it does. But nobody said that free speech doesn't encounter blowback. Okay.
It's consequence and responsibility
that's right. And so these companies have learned that sometimes when you do things for what you consider the right reasons, you better be sure that the rest of your people agree with you when you do it. Because if you don't, they're gonna blow back at you, and you're gonna lose money. And it's the same way with speaker companies.
John, what time is it around at your place?
Oh, it's only 1 a.m.
What?
I was gonna say
Holy
we've been doing this 4 hours, guys. Okay.
It's 11:30 out here.
Yeah.
I think you need to crash, John.
When
guys,
you can go on forever, Ron. I mean, it's fantastic.
well, in this case, well, my case, I'm at 11 a.m.
Oh, yeah, 11 a.m.
My day is just only halfway gone now. So,
But it's fantastic listening to you talk. I mean, there's so much knowledge that you gain from just listening to both you guys.
I'm sorry that it takes the last hour was 2 hours 40 minutes. This time's 4 hours. I think we're going to piss off a lot of people after a while.
I mean, a lot of people have left already.
Yeah, then there's people like Keith and Guillaume and Sam who stuck it out all the way through, and it's like, guys, thank you much for having such good listening power.
Thank you guys, and thank both of you for having such a wonderful session. And we're gonna maybe hold the next one whenever you guys are ready, and then we'll continue with our home theater design and speak about the hows and the whys of why we're doing certain things.
Yeah. Well, next time let's I don't know, John, do you want to do these separately or do you want to do them together again?
I don't know. Maybe I was going to come up with a joke, but I couldn't. I was gonna say, maybe we should do them separately, Ron. I don't mind, really, honestly, I don't mind either way.
I'm sorry, guys. I really tried not to do this.
We're still getting around to our design, Ron.
No, it's okay.
We still need to know where our surrounds go and where the Atmos speakers go.
What this is all about is about teaching and learning. We all learn, and while we're teaching, all of us do, and the people that listen to this will learn a lot. And that's all that I care about, honestly. I don't care about the highlight or whatever. I'm going to put this on my YouTube channel when I get the video when it's done too.
Yes, same way here too. So keep in mind, when you do these things to get ready for YouTube, please send us a copy of them in 1080 or whatever it is, and give it to us so we can download it and I can put it on my website.
Sure. This file is going to be a very heavy file.
You have to probably break it up into 4 parts of 1 hour each.
I have 64 terabytes of storage.
Oh wow. So anyway, I'm going to close the session. Thank you, gentlemen. Thank you so much. I mean, it's just been fantastic again. Thank you all who've stayed for 4 hours with us. I mean, I'm actually energetic, right? I don't want to go to sleep. I wanted to continue this discussion.
I know I'm going to be up till 3 for sure because I get wound up in doing this. And so,
Ron, look what you've done to us, Ron. I can just see phase. I can see phase balloons of diffusers now. That's all I can see.
Hey, welcome to my dreams. That's why I have to take a nap at 3 o'clock in the afternoon every day because my mind is like, and then because, well, I'm sorry, because I do most of my work, believe it or not, at night. So I'm actually up from about 10 or 11 in the evening until about 4 in the morning doing this, and then I sleep for a couple more hours. So so I don't have a sleep schedule. I have a what do you call it? A vampire schedule.
Vampire schedule.
Yeah. My schedule is well, you can sleep when you're dead.
yeah, that's kind of how I am too. John knows. He and I have been around each other long enough where if I see that I have a green dot on the messenger, he's going to get a phone call. It's like he may be in the middle of eating or having lunch or having a nap or whatever, but he's getting a phone call. So I think we talk to each other probably 4 or 5 times a day now.
Fantastic.
Yeah,
it's all in aid of science, and it's fantastic what you guys are doing. And I'm so glad that we can be part of this. And
we appreciate you guys doing this because there's nobody out there that would do this.
Masterclass is very important to all of us out here. I'm just very disappointed that not many more people attended. I mean, we have a very large fraternity, heavy fraternity out here in India, and And normally they do attend these classes, but I don't know, maybe
Well,
it's a Saturday
sounds
night
like
and
it.
they wanted to go partying. Maybe, I don't know.
Or maybe it's 4 hours long.
Yeah, no, I mean, then we didn't know when we started out, right? We were going to get done with that home terror quickly.
Yeah, this is why a lot of your guys like
we do it next time.
Fennel and stuff like that. They all say the same thing, that put it on YouTube because then we can watch it at our leisure
Yeah.
and break it into pieces and stuff. But
It is-
in reality,
yeah, true.
by posting these things, guys, you're doing the whole industry a service, and
Yeah.
we really do appreciate that, because
No,
without you guys, there's a lot of the stuff would never get out.
no.
Absolutely. We really appreciate that.
So
We,
we'll share
we appreciate-
some more. Yeah, we'll share more data with you as we get a chance to talk about it more, and I can put it into better graphic form so it's easier to see.
Like that, those balloons are so fantastic. You immediately came to know what that diffuser is doing. You know, that's brilliant. I think that's fantastic.
Well,
And it should become a standard, and more should
Well,
be, you know.
I'll
measured.
tell you what. Next time we do this, we have taken these balloons and animated them,
Okay.
so you can actually watch the sound move in the room and hit these diffusers and diffuse and do things, and we can actually
Nice.
show you. These
Very
are simulations. These are predictions based upon measurements.
Mhm.
Nice.
And we can show you a barrel, we can show you a QRD, we can show you all those things, the differences, and these are all done by one of the guys that we're working with, and they take 3 or 4 days to create each one.
It's
But-
it's very high computation, very computationally
yeah.
intensive.
Well, he's using a Cray.
Yeah.
Oh, you're a Cray. Wow.
Supercomputer.
Alright. Holy shit.
Okay.
Yeah.
So
It has to
we're
be
only
that
showing we're only showing about 0.3 of a second of time,
Right.
but it takes about a minute and a half to look at it.
Okay.
Okay, so when we come up next time, I'll have a few of these up on the thing that we can click on, and you can actually watch what happens. And we have them comparison, so you can actually put them in a room and see how they work in a room.
That'll be superb. That'll be fantastic.
Yeah. So if you guys think that these balloons are great, wait till you see these things.
Alright. Balloons! I got balloons.
John's seen them. He knows what I'm talking about.
Yeah. Brilliant.
So
So
yeah, we'll show you.
Yeah, let me just conclude by saying that we are really indebted to the two of you for sparing your time and taking this session. It's all in the aid of science, as you said, Marzi. But I think being able to talk to basically two colossi is something that we should be really grateful to. And of course,
Totally grateful. We are
so
humbled.
that's
Yeah.
we are really humbled.
Guys,
And
please don't refer to us as Colossus, because you remember what happened at the Colossus of Rhodes.
Oh yeah.
no, it's exactly
It fell,
what
it fell down.
It's exactly
Fell
what
down.
I know. So it's our way of acknowledging the fact that we are talking to domain experts. So as John pointed out last time, it's a question of the other side calling you an expert rather than you calling yourself. So I would still acknowledge that expertise, and it's our duty to acknowledge that. As far as I'm concerned.
We appreciate the expert. Okay. I know from my point of view, every time I hear Colossus, I think to myself, yes, and a few years later, the earthquake took it down and it fell right in the ocean. So it's like, I'm sorry, I don't want to be a Colossus. I don't mind being an expert.
All I can say, Ron, all I can say is that science is supreme, and so we are just students of science and students of science, and that's all that matters.
As long as you call me a scientist, I'm happy.
All right.
Okay.
Okay.
You've got the data. You've got the data to prove it that you're a
You
scientist.
got it. It's like, yeah, argue with the data. Don't argue with me. I don't care.
Exactly.
But yeah, so John and I will talk, but I would imagine, if you don't, as often as you guys want to have us, we're probably going to be available,
That'd be fantastic.
because our job, both of us, is educate, period. That's what we do. I'm 77 years old. John is much younger than I am. And
7 years younger.
That's much. My point is all we have left is to educate other people, because whatever research we've done will disappear when we die if we don't educate other people. You know,
Right.
so, and I hate to see that happen because there's a lot of time involved in that.
You not only
Okay.
got to educate, but you got to publish as well. You need to publish those papers and
I hate writing with a
That's
passion.
I know.
I've been on him. I've been on him. Yeah,
Yeah,
we're working on it. We're working on it.
Microsoft's
I-
got a very good text-to-speech converter, speech-to-text converter. So you could just
Yeah.
dictate it to your computer and then type it out, or use
Yeah.
ChatGPT.
My daughter keeps telling me that she's an author and she's published like 35 books. And
Oh,
she
wow.
keeps telling me, she said, Dad, she said, please just write it, just talk about it and let the computer figure it out. And I'm kind of going, so somebody said, well, these things that we're doing right now, we could break that up and take these and break them up into small pieces and put them together into a video book.
Yeah. Oh, that'd be great too. Yeah.
Yeah.
So,
Fantastic.
it's called, they have these AI things where if you have a
Right.
question, you ask the question. And then, me, when I'm 25 years dead, I can answer the question in video.
Like the
So
rings.
who knows?
Yeah,
Yes.
like the rings in the time machine.
Yeah,
Yes.
yeah, the rings in the time machine.
So who knows, Kartik, maybe we'll have to depend on you to write the book.
Yeah, Karthik, you can take that up. I'm always there to support you, bro.
and the youngest in the lot, so I hope that I take this. Yeah, it'll be a real honor to do that. But yeah, we'll keep at it. All I can say is that I look forward to having the next session whenever John and Ron, whenever you agree.
Well,
So-
let's find out whether your audience wants to come and listen to us anymore.
I don't think that's the issue, John and Ron. I think it's just a question of you having your dates sorted out, and we are good to go from your side, from our
Same
side.
time in a couple of weeks, I can do it.
Yeah, I
Okay.
can do it in a couple of weeks again too.
So I would say that maybe you guys discuss among the two of you, and we'll be ready when you are.
I'd say maybe first or second week of June
Yeah, that'd
would
be
be
great.
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 Yeah.
I think
Yeah, I
we
think
need to allow people to assimilate and absorb.
Yeah, actually digest what they've taken
Digest.
in tonight.
So today was a very heavy dose of information. I think
Yeah.
it'll take a lot of time for people to absorb because a lot of things have been unlearned today in terms of what people already know about acoustics and absorption
Yeah.
and diffusion. So I
It-
think
it-
a lot
it-
of unlearning.
Shapes.
Yeah,
I've
it takes
I've
more
learned a lot
time.
about absorption shapes and
Yeah,
diffusion balloons. Oh my god.
Look, guys, the simple facts are unlearning is harder than learning is.
Mm.
Yes,
Mm.
yes,
Okay, because this is two-step things. You have to unlearn and then you have to relearn.
right,
Learning is one part of it, but unlearning is very difficult
Right.
to do. And
right.
and this particular method that we're using here, I would imagine these people are all going to go home and they're going to have to decompress, kind of like going and diving under the ocean and having to come back up 1,000 feet. Okay,
Right.
they'll spend a lot of time in decompression. Okay,
Very
so
good.
It is.
So
It's the way you have to be when you do something like this. You have to set your bias aside and be ready to change your mind. When you
Absolutely.
go into a lecture or something, you go, okay, I know these things and I think I know them, but I'm ready to change my mind. I'm gonna, so like the little like the mutant said in Total Recall, open your mind, open your mind. You remember that one? So
yeah,
the
other thing is,
you got it.
yeah, John and I are both willing to say, look, we were wrong. The 706 proved that to us both. Okay, we both had the same idea that it wouldn't do low frequency very well. It wouldn't do this, it wouldn't do that. And by testing it, we both had to sit there and eat crow.
Yeah.
Okay. Even on Facebook, it was like, okay, guys, we were wrong. This is probably a better than this type of thing. You have no idea. At some point at our age, it's kind of like, oh God, here we were wrong again. And the older we get, the more wrong we are more often. And all you can do is throw it away, pick it back up, and relearn it, and go back and say, okay, guys, we were wrong. Here's the latest data. And will it change in the future? Maybe, but it hasn't right now. This is the latest information we have. And all we can do is teach the latest information we have. And at some point, if better information comes by, hey, you teach it to me, you show me what it is, I'll be happy to look at all the data. If the data says yes, then I have to change whatever I'm doing because that's the facts, whether I like it or not.
Right.
And you have to have people willing to do that. And John is very willing to do that. I'm willing to do that. I'll argue until I'm blue in the face on my point of view until you show me that I'm wrong. And when I'm wrong, it's like, oh, wow, okay, yeah, I'm wrong. So yeah, okay, let's go with yours and I'll throw mine away. You know, but you damn well better be able to show that I'm wrong.
At the end of the day, Ron, science has to win, and science will win. That's the whole point.
That's the whole point. Is facts do matter.
Right.
And science doesn't care what you think.
Right. It's absolutely. It's agnostic to what you think.
Yeah. Well, there was a science fiction book. I'm trying to remember, was it Asimov or Arthur C. Clarke? The moon is a harsh mistress. Science is very harsh. It doesn't care. If it hurts your feelings, sorry about that. Get over it. Okay. So yeah. So both John and I are both believers in science, and it doesn't matter what you think or what you think you know, or what your interpretation of it is, or what your extension of a science fact is. But one of the problems is we come up with a simple fact, and then people run with it like crazy and extend it 15 different directions where it may or may not extend those directions. Okay. So that's one of the things that happens is we do all this extension, like, you know, we'll say, well, it does this. Well, if it does it for 6 feet, it must do it for 9 feet too. Well, no, not necessarily. Okay.
Right.
You know, so, and that's what we do all of our measuring for, is to prove, you know, how far can we carry this, or how far can we not carry this?
Right.
So yeah, thank you very much for giving us this method of platform.
We can only thank you, Ron and John. So yeah, we are just a medium in trying to get this knowledge out to the world. So we are just
thank you for the medium.
Yeah, we are trying our best.
Thank you for the medium, because it used to be all we could do was reach a few people in a classroom, and that was it.
Right.
Yeah.
Right.
Now we can reach hundreds of people this way, or thousands of people, especially on YouTube. Yeah, because if it goes on YouTube, it must be real.
Absolutely. Absolutely.
Hell yeah. You know,
especially with 4 hours long, you know.
Well, it's like when we're working, you know, Ron mentioned to me earlier, you know, acoustics doesn't happen in a vacuum.
That's like that one.
There's a profound
statement about that. Yeah, I said, yeah, there's no acoustics in a vacuum.
No acoustics in a vacuum.
So just
all right, guys.
Closing up, just one last thing. If you know, remember to talk about the LRAD that was used in the Avengers movie, the Hulk. If you remember.
Yes, that's right. That's right.
It was used in the Hulk.
All I know is I got him up here and I unpacked him and I put him up, and I went down the end of my test building at 700 feet, and I thought I was going to get my head ripped off.
All right. Wow.
You know, because we were projecting it down the length of it. And usually you go just a couple meters past, and it drops down to 50, 60 dB. And it was like, I'm sorry, but I measured it at the surface, and then I measured it out there, and it only dropped like 3 or 4 dB over 600 feet. Wow. And it was like, what the heck? You know, and then I realized what it was. It was a focusing function, you know, and then we started looking at it, and it's like we do lasers and stuff. And,
coherent beam.
Yeah, it's a coherent beam, and that's coherent beams are scary what they can do.
Yeah.
You know, there's some things coming that I can't really talk about too much, other than the fact that they are coming.
Yeah, they're coming. They're coming. I know about this being from that industry too. So yeah.
There's things coming in, lasers and weapons and stuff like that. And it's like, I don't think I want to be in the other end of it.
Right.
Yeah. So it's like, no. So, you know, I always tell John, I always complain about being 77 years old. In some ways, I'm happy I am, because I may not have to live through some of that stuff.
And on that cheery note.
Yes, let's go on our way now. Okay.
So thanks a lot.
Good night.
Take care.
Good night, John. Good day, Ron. And thanks to everyone who attended. We'll see you soon. Thank you.
All right. Sounds good. Thank you.
Thanks.
Bye.
All right. Bye. Bye.